Hello, everybody, and welcome back to another day of invertebrate zoology. Today we are covering the echinoderms. Echinodermata seems like a kind of anticlimactic animal to land on at the end of all this invertebrate study. It doesn't seem like it would be the kind of pinnacle species that we'd be talking about, but they undoubtedly are from an evolutionary standpoint. They've got a lot going for them, and again, hopefully, as is a common theme throughout this course, you're going to find there's a lot more going on with these animals than initially meets the eye. They are not just iconic souvenir things you'd find in a gift shop. These animals have been able to etch out a living for themselves using arguably the most efficient system around their own environment. And we're going to talk about all that. So, echinoderms is where we are. Echinoderms include the asteroids. That's the one we're going to be focused on. Those are your sea stars. Brittle stars, the echinoidea, which is urchins, and again, you're probably more familiar with some of these animals as gift shop souvenirs versus live animals. But sand dollars fall in there as well. The holothurans, sea cucumbers, very cool animals, very, I don't want to say underrepresented in zoo collections, but certainly underutilized as far as a talking point. A lot of these animals are so valuable from an education aspect that you should be able to give a good keeper talk working at your respective facilities on any one of these echinoderms, should you be fortunate enough that they are featured where you're working. And the last one, sorry, crinoidea, sea lilies, and feather stars. So, couple key things to point out here. The bread and butter of these species really ties into the water vascular system. The water vascular system is going to be incredible with how these animals are able to move, how they're able to operate, how they're able to acquire food. And their regenerative abilities are pretty high up on the list as far as amazing adaptations these animals have been able to develop throughout evolutionary history. Their namesake, though, really falls with that five-part body plan in the water vascular system. The other unique trait for these animals, and the reason they're kind of popping up, I guess, at the end of all the animals we've studied, all of which have been incredible, I think, is deuterostome development. These animals are considered lesser deuterostomes, so on the low tier, but evolution-wise, that brings us really close to the new development of animals that more than likely you've studied and want to work with. Deuterostome development is extremely important. Who can tell me a little bit more about what deuterostome development really entails?
So there's gonna be like two different. So you're gonna have protostome and deuterostome. So previously it was protostome where the blastopore develops into a mouth, whereas deuterosome means literally like mouth second. So that blastopore is going to develop into the anus, and then the mouth will come second. Which really plays a big part in like this water vascular system and having like two entrances and I guess openings um, and Mom, and having that mouth develop second, whereas they are developing um, the anus first and having a whole. I lost my train of thought. I'm sorry.
No worries. And yes, this is arguably one of the strangest things to uh, pat yourself on the back about. It's very like I'll put it this way: like I doubt anybody's gonna hang up a trophy or an award that I developed my anus first, and that goes on the wall of fame. It actually is a big deal, as silly and comical as it sounds. Deuterostome, again, as was mentioned, means mouth second. And so I'm going to demonstrate this through an amazing drawing, as always. Picture this. If through protostome development, you develop mouth first, Actually, let me change colors here. Get out of here. If we develop mouth first, that means you're able to take on food. Very quickly, you need an excretory system in order to get rid of that excess food. So very quickly, you go mouth, anus. I know, super exciting. It's exactly what you all want to learn about first thing in the morning. But you very quickly have to develop an excretory system, and that shortens the length or the span or the complexity of what could be a true digestive tract. If we develop anus first, and again, if you guys really want to, you're more than welcome to. I can send you out a cool award certificate. You can definitely display it at your house and explain how you're a deuterostome and how amazing that is. I don't think it needs to be bragged about, but it should be discussed. If you develop anus first, it actually allows for this complex digestive tract to form before the mouth forms. So for us, let's just assume I guess intestines would be the easy part. Assume intestines, stomach, liver, kidney, all these filtration processes that can occur, and create a much longer segment to actually wind up being the digestive tract, leaving the last part being the mouth. You're able to develop a lot more. You're able to bring a lot more into the proverbial folds when you're a deuterostome. And while these animals, again, do sit kind of at that low tier of lesser deuterostomes, um, it still counts. It's a big evolutionary adaptation. Uh, Probably not the one that people brag about, but really of note, and it's the reason echinoderms sit kind of at the almost the end of the list as far as invertebrates go. They are, and we still got a couple of animals to talk about, a couple of different species, but they're about as high up on the list as far as invertebrate evolution as we get. Nobody has a picture of a sea star on their mantelpiece and say that's my great 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 grandmother, but it's true. That's the most logical jump in evolution is this deuterostome development. So that brings us to, aside from the water vascular system, we're going to start here, the 5-part body plan. Couple things of note here. The 5-part body plan it's Echinoderm 101. It's exhibited throughout every species in here, no matter what the external visual appearances. We're always going to have the body built in a 5-part body plan. What's unique with this is that means we have indirect development because the larvae themselves are free swimming and bilateral. Bilateral meaning, of course, that you can basically cut something down the middle and have mirror images. To be honest, the ciliated part, that's usually that flagellated appearance. It looks very similar to, I guess, a sperm, where we have a central mass and a flagellated tail that can move them along. And then we'll switch to that 5-part body plan. So very big developments as far as this shifting, I guess, into a 5-part body plan around that central axis. And we'll discuss this a little bit more with some visuals, but here's the text you need as far as putting it into words. And then, yeah, we'll take a look at a few more pictures, and hopefully that gives you a better sense of what's really going on. So this image, and hopefully it's coming up clear enough for everybody. We see that 5-part body plan because of the arms, or what are called really the rays. But if you look closely, you can see this development here of the 5-part body plan. That's a great drawing. I did that sea star justice. But you can see that pentaradial symmetry of the 5-part body plan developing in that central axis and then moving forward with the 5 rays that exude off the animal. Again, you can see it right here in the center of this sand dollar. Um, I agree, it looks nothing like a sea star, but we see that same pentaradial symmetry developing even in an animal like this. At the bottom of your screen, we have sea urchins with the spines removed, and you can again see a 5-part body plan. This is what's, I guess, not tricky, but a little tough to keep in the back of your mind as you study echinoderms or work with them. Uh, no matter the external appearance, again, a sea urchin with spines, you're never going to think, hey, this animal's built in a 5-part pentaradial symmetry plan. They definitely are. Sea cucumbers are another one that's tricky. They look like a tube of sausage, basically. Not knowing that they have this 5-part body plan, though, is a disservice to you and your knowledge as a keeper. You got to understand this pentaradial symmetry and how it folds in to everything that makes echinoderms work, and they're extremely efficient at it. So they're doing something right. This is one of those kind of rules of thumb. It because of the natural processes and natural forces that occur, of course, you're never going to find every single echinoderm across the board being built in multiples of 5, but that's the baseline. That's your general rule. So, meaning if you have, take a sea star, that's your easiest example. Obviously, they have 5 rays or arms. Uh, if we have more than that, they're going to be built, in theory, barring injury or mutations or deformities, they're going to be built in multiples of 5. So you have maybe 5 arms, maybe 10, maybe 15. And you guys can do the counting from 5 from there. But in theory, all these animals are built in multiples of 5. So you could have 100 or 95 uh, arms or rays or extensions of the body, but it's always built around a new 5-part body plan. So initial 5 parts, 5 more, 10 more, totally acceptable, but you're never going to grow like, let's say, 6 arms or rays. Uh, it's always built around a new axis and a new 5-portion body plan. So let's move on to the way these animals actually function. They're going to exhibit what we call taxis. And this is going to be a really key term to learn and understand. Um, just based on how these animals behave. Again, if we go back to the roots of everything, what makes an animal an animal? A big part of that, a sexual reproduction in some format, um, and response to a stimuli. But taxis is the key term used here, and I don't know. I guess who can tell me a little bit more about why we would use taxis as opposed to just movement?
So taxis is actually the way that sea star or I'm sorry, echinoderms orient through their environment. It's the general directional response to a stimuli, whereas other forms of response to a stimuli. Oh, I can't talk today. I'm sorry. Such as kinesis is just a movement response, where and taxis, like I said, is a directional response where they orient away from or towards. And there is a whole list of different classifications of taxis respective to their stimuli, such as wind, chemical cues, light, gravity, pressure, temperature. There's many more. Essentially, like I said, it's the way that they orient through their environment, utilizing cues from the environment because they don't have eyes. So basically, it's like their eyes, their brain, and like their nervous system all in one. Um, for example, if it helps kind of clarify what I had just said, if you have an echinoderm, let's say a sea star on a rock formation underwater, it's underneath. So like the formation is maybe curved, but it's very tall. So it's on that bottom side of the curved area. It's probably there for hiding or what have you. It's being a sea star. It most likely utilized the lighting, and it can feel how do I explain it? So just bear with me. In layman's terms, it can feel that it's being pulled, so it's on the underside of a rock, but also maybe not on the bottom part of the ocean floor, like the ocean floor, um, and in like a darker area, as opposed to being on top of that curved part of the rock structure where the light would hit it more. So in a kind of anthropomorphizing way, it knows that it's possibly hidden. It can possibly get rest in that kind of darker underside of the rock structure, etc. I hope that makes sense. It's just in a nutshell, again, the way that it orients through its environment, utilizing environmental cues rather than having eyes to tell its brain what to do.
Yeah, like excellent explanation. The directional response, the movement towards or away from, we categorize those as positive or negative. So towards is positive, away from is negative. And I think it was mentioned too, one of the big things in there, the chemosensory or the water quality parameter function, you get a buzzer going off that says good or undesirable. And one of the tough things to understand with taxis is it really is kind of the eyes, brain, ears, nose, everything, all your senses all in one, because these animals don't have that centralized brain. They don't have the component. I don't know. Let's just trust me, guys. I by no means am good with technology, but basically a bunch of wires, but there's no motherboard to connect to. I think that's still a relevant term. There's not a centralized uh, brain or a motherboard dictating, hey, let's move towards or away from something. It's the entire body is able to pick up on this cue. Again, we mentioned a ton just now. Light, temperature, magnetic polarity, like you name it. Uh, and the body's going to have to kind of just make a choice on its own because there's not that central. We'll discuss the CNS in a little bit, but there's not that centralized decision making part of the body. And so that's where the term taxis comes in. Taxis basically being a directional response to a stimuli without a brain, without something directing that to function that way. You know, you can still adapt and make change in the environment, um, but it's not a, and again, anthropomorphizing wise, it's not a decision the animal's making, it's a natural instinct or behavior. Think of it the same way as what we call that knee jerk reaction. You can't stop your knee from popping up when the doctor hits it with that hammer. It's a response that's going to occur no matter what. That's basically the way taxis works for these animals. You're moving towards or away from a stimuli without the motherboard telling the body to do so. It's a knee jerk natural instinct, a reaction to the environment. So we're going to talk about a couple of them. The first one we're going to start with is phototaxis. This is going to be very common in sea stars, especially, and occasionally urchin species. But the positive or negative, towards or away from, that's the way we define it. If, and let's say we're working at our respective facilities, maybe I have a tank with a light at the back of it to backlight the tank. That way guests can see everything. If our sea stars are navigating towards the front of the glass, they're exhibiting negative phototaxis. So they're moving away from the light. Should they start aggregating around the light, that's exhibiting positive phototaxis. And of course, there could be other causations and effects occurring there. Could be that maybe the lamp is giving off heat, so in that case, you're exhibiting a positive taxis towards that heat source. But you guys see, hopefully, the directional movement without the brain telling the body what to do. That's what we talk about with taxis. So phototaxis is our first one, towards or away from the light, and we label that again as positive or negative. With geotaxis, this is one of those that's probably a little understated with how important it is and how much it makes sense. This is movement along lines of gravitational force, so polarities, um, north, south. The other thing that's important to note here is, again, take yourself out of that mammal mindset of here's north, here's south. We all know the mountains are at the west because we live in Colorado, and that's very helpful direction wise. But if you're a benthic dwelling animal that lives on the seafloor, uh, it makes a lot of sense to use gravitational force because now it's telling you depth. You're not only going north or south, you're also figuring out where, let's say, like a coastal drop off occurs. You can tell as you're getting closer to basically the Earth's core, really. And so you're gauging your depth as you go using this geotaxis method. Again, very helpful for animals that almost spend their entire lives, aside from their free swimming larvae form, buried in the mud and moving along the ocean floor. Pretty important to have a depth meter that can sound the alarm or go off when you know you're either going too deep or maybe you are migrating to a deeper benthic environment. So geotaxis, definitely important here. Despite being these brainless animals that are just responding to stimuli with a directional movement towards or away from, we do have some pretty unique defense mechanisms here. The most common is what we call defensive posturing. Again, just like it was mentioned, we have a directional alignment, in this case, towards a stimuli. So let's say your finger or a crab, something's coming in here, bothering this animal. The spines are actually going to orient themselves towards that negative stimuli as a defense mechanism. And let's be honest, that's a pretty cool move considering this animal doesn't look particularly cuddly or snuggleable. That's a word. Nobody really wants to snuggle up to it initially, but if the animal's receiving negative stimuli, it's going to orient all the spines, kind of send all the troops to that front line and orient themselves to really deter that predator. And so, again, another indicator that we are talking about a living animal. It's responding to a stimuli, but their defense mechanisms, I think, for as slow moving and benthic dwelling and almost sessile as they are, really lends itself well to explaining how these animals function and what they're able to really do when it comes to defensive posturing and taking care of themselves. The other defense mechanism, which is one of my favorite, is auto-evisceration. If you break those words down, you might be able to figure out what we're talking about. But can anybody elaborate on auto-evisceration?
So evisceration is going to be like the ejection of the internal organs. So basically, like in sea cucumbers, you'll see them kind of just shoot their internal organs either out their mouth or their butt. And that either is going to confuse whatever is after them, like predator wise, or predator's just going to eat that. So that's really like a solid method of that gives them time to get away. With sea cucumbers are actually able to like regenerate that internal organ that they've lost. Whereas like with starfish, you'll see them kind of push their stomach out and then they're able to retract it back in. And that's them choosing to, which is going to be the auto part of the word. Versus like if humans were eviscerated, that would obviously be something we weren't choosing to have happen. So
Yeah, perfect. And yeah, excellent explanation. The auto part, meaning that they are choosing to, yeah, there's no better way to say it. Eviscerate themselves, expel the internal organs. Again, if we went back a couple slides, what are some key traits for these animals? Water vascular system and regeneration. So it is a unorthodox but very effective method for self-defense. Probably going to be exhibited most in the holothurans, so sea cucumbers. Predator comes up, you're getting bothered, instead of having chunks taken out of you or being eaten, you expel your internal organs. The animal either has something to eat, the predator has something to eat, or there's always the chance, assuming, let's say the sea cucumber has been eaten really well, could be kind of a vile mass of waste product in the intestinal tract and things like that. So it could really deter or turn off the predator from eating at all. But either way, you're achieving the same results. Either the predator gets what it wanted, some food, or it's disgusted and never wants to come back and visit your restaurant. And because of that regenerative ability, it's really at no detriment to you, provided you can be left alone long enough to start recouping the energy to create those internal organs. You're going to be just fine. The one time that this weird plan of auto evisceration kind of falls apart is if you were constantly being predated upon, or predator didn't fall for it the first time, comes back for seconds. You're obviously not going to instantly have a new digestive tract to expel from the body. So it's kind of a one shot at a time type of deal, where the animal can use it, hopefully get away, and yes, they can move, not very fast, but you've given them something, the predator, something to work with. But you're going to need time to recoup your losses and redevelop that digestive tract in order to later auto eviscerate again for a new potential predator. So that kind of covers our general overlay of echinoderms. We're going to focus on sea stars. They're the easiest to identify and look at and explain. But keep in the back of your mind the whole time we're talking about this, every one of these animals follows the same build, body plan, and most importantly, the water vascular system. So sea stars, and again, they're sea stars, not starfish. Sea stars are called asteroids. Super cool name. We get to talk about asteroids and rays and all sorts of fun, common speak lingo that's actually scientifically accurate. So that's always fun. But we're going to focus on asteroids. Again, though, I know I just said it, but I want to reiterate it. Keep in the back of your mind, this is true for all echinoderms. They're all going to follow the same builds, no matter what the external appearance is. So, again, they're sea stars. If you call them starfish, you're not getting kicked out of the cool fish club, but know that there is a very distinct difference. Starfish kind of garners up some incorrect terminology and imagery of what these animals are related to. Sea stars helps us keep things clear and know that these animals are indeed Echinodermata with that 5-part body plan. And with that comes the pentaradial symmetry. Depending on what you're reading, where you're researching, you'll hear it the names are all over the place, but we're really looking at 5 parts. And again, just to kind of rehash what we've talked about before, if there's more than 5, it's going to be 5 more or 10 more. It's almost a cloning or a reproduction of that 5-part body plan stacked on top of one another. So always in multiples of 5s. The African, this is a red knob sea star right here, but does a great job visually for us to show what we're really looking at. And while we have 5 distinct rays, red's probably not the best color there. Let's go with green. Well, we have these 5 distinct rays. The thing I want you to look at that the sea star here does for us is it's 5 parts around an axis. The axis is what's important. This is where that initial pentaradial symmetry stems from. The unique trait here, and again, this is why regeneration is so effective for these animals, and the asexual reproduction, the cloning, things like that, is every single one of these arms or rays is basically a clone of itself. And this is where sea stars have the upper hand versus the rest of the echinoderm gang. With, let's say, a sea urchin. So, same body plan, but we're taking off these arms or rays and just focusing right here. You've got everything kind of contained in one central household unit. With sea stars, we've got clone arms, basically, where this ray right here possesses the exact same internal workings as this arm, uh, meaning we have digestive and reproductive glands in every single ray. So a severance here means that you've got two individuals that still can function the exact same. I've got digestive and reproductive glands. Here I've got digestive and reproductive organs. And so it's basically diversifying your portfolio, if you will, by spreading it out over 5 rays. Every one of them performs the exact same tasks and functions. So very efficient animals in that regard. Here's the cool imagery I was talking about that we discussed a little bit more about bilateral symmetry, moving on to pentaradial symmetry or radial symmetry. I love personally the image down here. I laugh every time we do it every semester. Just a cool Google search of symmetry, and for whatever reason, these people thought that a lobster, a shovel, a flower pot, and an anemone would be excellent examples. I don't know who gave him the thumbs up to put the shovel image on there, but it does get the point across. But there's a lot that goes into this strategic movement from bilateral symmetry to pentaradial symmetry and what it really means. So, given the goofy little image down there on the bottom, can somebody elaborate on that shift from bilateral to penta or radial symmetry?
So first things first, echinoderms have the pentaradial or pentamerous symmetry. And this is, I'm sorry, can you guys hear me okay? I feel like my mic is being crazy.
No, you sound good.
Okay, good. Sorry about that. This is a body symmetry in which the body can be divided into 5 equal planes intersecting at a central axis. It's a type of radial symmetry, but indicative of one second. It's indicative of goodness. Lost my train of thought. It's indicative of 5 planes specifically, whereas radial can be 4 planes or more, such as dividing a cylindrical bow plan into like 50 or more different planes. Did I lose anybody? Sorry about that. So bilateral, meaning two-sided, simply means a body plan only that can only be divided down a central axis and not in different ways, such as the shovel. You can see if you take one of these intersecting planes and throw it through the shovel, the head and the handle do not, mirror each other. So basically, in a pentaradial symmetry, they mirror each of the planes mirror each other and intersect at the central axis. And what's interesting about the body plan of echinoderms, is that the development stages of the truly reproduced offspring go from bilateral to the pentaradial symmetry. Did you mind, Alex, if I went into that, or?
Please, by all means.
So with pentaradial symmetry, the offspring typically, like I said, will start at bilateral, and during the blastula stage, after it hatches, it's free swimming, right? Juvenile rudiment. Through the metamorphosis of the freshly hatched blastula stage, through the gastrulation and into the I forget what it's called, the bipinnaria stage. Am I saying that right?
Yep.
I'm sorry. I'm like trying to go based off of memory. There are two major things that happen through those three stages. One is the body axis shifts completely. So everything internally in that larval form of a starfish, as an example, is setting the blueprint. Okay, which way is up, which way is down, and then this is where we're gonna put our innards from there. So everything, the body axis shifts, everything is moving around that central ring, and then and that process is actually called torsion. So torsion is just after the body axis shifts, torsion is just continuously happening through the rest of the development stages until the larva kind of like makes this like shaft where it or stalk, and it attaches to something where it can safely finish development, and then it breaks away as like its own independent little starfish. It just completely, it's almost like cutting the cord, in a sense. I hope that you guys are following, and I hope that I'm like staying clear on the path of what Alex, what you're hoping I'm gonna say. But yeah, so until the main pentamerous body plan has become established, it's going to be on that stalk. From there, the rudiment sea star cuts the cord, so to speak, again by breaking away from its attached stalk, and starts to finish its development into this this the pentaradial symmetry.
Yeah. Oh my gosh, that's better than I was going to go in detail with you guys. So yeah, spot on. The I love the imagery of the kind of that central stalk, I think was the term used. Excellent visual image of what's really happening. This, and I'm going to do a terrible drawing that's much less explanatory than the lesson we just learned. But we have this ciliated, again, kind of sperm-like appearance. We get this division down the middle, usually at the cost of the right side being absorbed by the left. But this stalk is right here, and all of a sudden this becomes, you guys remember the term torsion? I'm glad we got to use that again. You guys remember that from talking about mollusca and what we call whorls. Remember the spirals in the shells themselves? Shells themselves, that's a good one. This torsion and the development of the whorl, it's almost a, and again, I think stalk is a great term used. It almost, if you guys are kids and you had one of those cool paint mechanism circle whirly deals, you put a circle piece of paper, the thing spins it around, and you drop paint on it, and the paint almost symmetrically radiates out from that central axis. Kind of the same idea here. In that center, the part that's spinning, that's the stalk that was mentioned earlier. That's the part where everything twists and starts radiating outward from, but in 5 parts very specifically. And that idea of going, let's look at the cool shovel image. Bilaterally means we have 2 mirror images. Take a butterfly too. Don't literally cut a butterfly in half, please. But you understand that butterflies are going to look the same. It's going to be mirror images of one another. The reason pentaradial symmetry is so important is we truly have mirror images of itself. It's not like if I bisect this animal any direction, let's say I take this axis right here, it's not like here's the heart. That's a great heart. That's why I didn't get picked for Valentine's Day. Here's the liver, and over here is maybe the intestines. Like, we literally can bisect this animal any which way and have mirror images, the same exact crop of internal organs, reproductive gametes, digestive tract, etc. All are going to be mirrored every way you slice it, basically. And so that's where that pentaradial versus just radial symmetry comes into play. As far as the terminology we're going to use, again, I feel like we just got a great explanation of how this five-part body plan presents itself. Presents itself. Um, but we're going to have what's called a stellate shape. Stellate is just the collegiate level term for star-shaped. Um, a stellate shaped body with a central disc that everything, again, kind of torsion and whirls off of to create this five-part body plan. The most notable aspect that's visually observable for us, that is the umbilical groove. This is on the underside of the sea star. So, and again, assuming you probably haven't worked with a lot of living sea stars, picture your typical gift shop sea star. If we flip that animal over, so we're looking at the underside, the ventral aspect that would be pressed against the sand typically, or against the substrate, we're going to have these V or U-shaped furrows running off from that central axis, looking like this. Again, this is looking at the what we call the oral surface. You're going to have these grooves. This is kind of the, I guess like an aqueduct would be a good explanation for it. It's a structure built in place to help stabilize and support the water vascular system. It's much more than just, oh, look, I have these weird furrows on the underside of my body. It's the like framing, I guess, if we want to use a construction analogy. That's the framing for the water vascular system to sit on, run on. It's, again, picture like a house being built. All the heating vents that run through your ceiling, they're sitting on something. There's studs and various pieces of drywall or soffits or things like that that are all there to support the internal workings of the house. Internal workings of the animal are exhibited here. So it's much more than just a aesthetic groove. It truly is kind of the functional support. These are the joists or the rafters that help maintain and help stabilize the integrity of the water vascular system. One of the weird things, and I think we'll just talk about it right here because it's a good place to stop and talk about it. One of the hardest things to understand for people is what we call the oral and the aboral surface. It's dorsal and ventral, so top and bottom. But, and hopefully you guys are following me for this. So let me know if it doesn't make sense. One of the craziest things to understand and delineate with these animals is here's the mouth. That's the oral surface, right? The underside of the ventral aspect. If I were to flip this sea star over, on the top, almost right above the mouth, is the anus, the excretory system. They, like, let's just take a random dried, typical gift shop sea star, for example. The mouth and the anus are probably, I don't know, an eighth or a quarter of an inch apart from one another, but they couldn't be any further apart based off the animal's true biology. And this makes it difficult for a lot of people to understand. It looks like you're almost connected mouth to anus. Like there's such little space between the two. But remember, as was mentioned earlier, I think one of the first couple slides with that deuterostome development, they're actually the furthest apart from one another. Reason being, here's the mouth. If the mouth takes in some food, it's got to travel through this digestive tract. Here, 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 and then is expelled through the anus on the aboral surface, the top side of the animal, the dorsal aspect. And that's it's a tricky thing to just keep in the back of your mind. Despite the fact that arguably the mouth and the anus are probably the closest orifices on the animal in relation to where they're located, they're actually the furthest away. any food that comes in has to travel the entire body, it has to run the 1600 meter or whatever you want to call it. It has to run an entire Olympic event to make it to that excretory system, being the anus. And that I think is it's difficult to process because again they are visually so close and they couldn't be further away. They're miles apart based off how the animal's oriented and laid out, and that's the advantage when you get to that deuterostome development. That's the reason it's so important. That's what's really going on. That's an extremely complex digestive system in order to make its way all the way to the terminal end or the finish line, if you will, even though they look visually like they're right next to each other. One of the main concepts here, again, is that copying of the 5-part body plan. If an animal is going to go up, it's always in 5s. And one of the animals most notorious for this is the crown of thorns. Crown of thorns sea stars. There's a lot to talk about there. They're going to come up quite a bit in the lecture. The size, diameter of both the central axis and the rays themselves can vary. Rays is highlighted here because that is the proper term. It's very similar to what we talked about with cephalopods, where yes, everybody wants to call them tentacles, but they're labeling is important as to what is an arm versus a tentacle versus like a hectocotylus and things like that. So rays is the proper term when talking about these stellate shaped sea stars. Oops. On this slide, you can tell the vast differences here, both in size, shape, formation. At the bottom right of your screen, that is a sun star. A cushion star is to the left. They're not the typical, we usually just call them pancakes, pancake sea stars. It's not the typical body plan, but even looking closely at this one, you can still see that 5-part body plan at the top of the screen. And with the big title right next to it is the one, the only, the crown of thorns sea star. They're going to come up a lot, and it's for an important reason. Does anybody want to try to go a little more in depth as to why crown of thorns is going to be highlighted again and again?
So there's a couple things that are really cool with the crown of thorns. First, they are going to get their name because their spines do look like thorns. They're like one of the largest starfish, which is pretty cool. You can see that central disc with like their arms coming out. So a lot of people, they don't really look like a starfish. And they do get that name like crown of thorns more for how they look. So they have toxins in their spines, well, some of them do, and they have no method for injecting that, which is pretty cool. So it's really just going to be if you get like if they were to touch their prey or to like basically like stab them, it's the piece of the tissue that holds that toxin that then gets stuck in the flesh that is going to cause the issues. But their main whole like what really got me into crown of thorns is they actually eat coral, so or like the stony corals I should say, and like hard corals. So their main like their body plan really needs to be flexible, and they are like prehensile so that they're able to go into like wrap around that coral. And a single crown of thorns can consume about 65 square foot of coral a year. So they are like a really big issue going on with the destruction of coral right now.
Yeah, and they are kind of, I guess, intriguing or pleasing to look at because they do look, as far as sea stars go, like they're arguably some of the most magnificent sea stars out there. They're definitely like prom king. Their faces on the front of the yearbook, aesthetically pleasing, very interesting to study. I love that the toxicity and the spines themselves were brought up. Man, they're just ravagers, though. They decimate coral populations. Later on, we're going to talk about crown of thorns. Again, will pop up quite a bit. Later on, I do want you guys to keep them in the back of your mind because they're going to pop up when we talk about reproduction for these animals. And yeah, crown of thorns really have it's one of those where you kind of like the bad guy. They're so efficient at what they do. Yes, unfortunately, it's decimating coral populations. That's what they do best. But you almost got to hand it to them. They're that bad guy that you almost kind of have to do that slow motion head nod for, like, yep, that's the old crown of thorns doing their thing. And yeah, unfortunate that it's destroying ecosystems entirely, but they're really good at it. You got to tip your hat to them. So they will come up again. So don't let crown of thorns venture far from the back of your mind as we go forward. With the taxus that we discussed earlier, this, unfortunately, in the times of online teaching, would have been very easily to demonstrate in the classroom back when we had dissections and things like that. But you've probably done something like this maybe in your junior high or high school years, if they still do dissections in bio class, things like that. The rays themselves have what we call an optic cushion. The optic cushion it's usually red tinted. These are going to be the light sensitive cells that allow these animals, again, without a brain, to detect where light is and move towards or away from it. Again, exhibiting positive or photonegative taxis. The away from, how do I want to word this properly? The away from light, yes, that's kind of useful, but think about it. The real setting these animals are in. If you're in the ocean, what does moving away from light really mean? It means deeper. So there is something to be said about light and dark and day and night, but really you're talking about depth more often than not. If you want to move towards the shoreline, you're going to exhibit positive phototaxis and move towards the light because that means you're getting into shallower water. Sun is able to pierce the water easier, and so you're moving depth-wise as opposed to really light-wise, if that makes sense, if that's worded okay. So optic cushion allows them to move towards or away from light, but really that means depth. And of course, sometimes temperature, depending on what species we're talking about. You guys, if you think back, hopefully remember a term just like this from the Peripherin lecture. That was the term spicules. Spicules are the calcium carbonate plates that make up the structure of the mesohyl of a sponge. Here we have almost the exact same concept, but more rigidly assembled. And these are called ossicles. So I guess the way I would put this is think about peripherins. They basically drop off tiny pieces of calcium carbonate throughout the mesohyl, again, air quotes, the tissue of the animal. That helps give them their rigidity. That's more like putting a bunch of sticks together and making a fort, whereas ossicles make up more of like chainmail, linked and much hardier calcium carbonate plates. The key here that I really want to point out with the ossicles, as opposed to the spicules in sponges, we need varied function from these calcium carbonate plates. Again, we're invertebrates, so we don't have a true skeleton, but we need as much rigidity as possible with as much flexibility as possible. And I realize that's counterintuitive, but that's what makes echinoderms so effective, and they've been doing it for a long time. You need to be extremely rigid, but have flexibility for a multitude of reasons. One, you need to be able to manipulate the body in a variety of forms, both pancaking, I guess is the term we'll use. So you need to be able to squeeze through and in between stuff into crevices. You need to be able to envelop and wrap around your bivalve prey. And again, depending on where you grew up or if you visited beaches, things like that, you see a lot of your sea stars in intertidal zones. So areas where waves are crashing in, the animal stuck to a rock, it needs to be able to absorb that blow. It's a bend but not break strategy, if that makes sense. You've got to have this chainmail that's extremely flexible but extremely rigid to withstand some of the trials and tribulations these animals go through. So while we're talking about the way they orient almost this exoskeleton for this spiny appearance, these spines are serving a purpose too. All the little, again, pores almost that you can see. Picture, again, we're going to use the gift shop sea star for an example. It's almost sandpaper like. You can tell that there's very obvious peaks and valleys, rises and fall throughout the skin. These are typically the papillae. Papillae makes up what I think is one of the grossest terms, skin gills. I even hate saying it. I get, ugh, I'm shaking right now. But dermal branchiae, the technical term, skin gills is exactly what they are, though, and it's not fun to say, but it's very, very accurate. This is going to be the site for respiratory exchange, bringing in oxygen, giving off CO2. Again, and I know I've harped on this every time we talk about how gills work, but it won't hurt to do it again. Just keep in mind every time you have a surface of the body, and this is true for a ton of your inverts, especially the aquatic ones. Amphibians are the same way. All of your fish species. Anytime you bring in oxygen, there's always the passive byproduct of releasing something off into the ocean or the environment around you. In this case, you can bring in oxygen, give off CO2, and you're quite literally breathing through the entire skin layer on that dorsal aspect, so the top side of the animal. To be totally honest, there's also a lot of gas exchange that happens with the combination of the tube feet, but we'll talk about that shortly when we get to the water vascular system. But the entire animal is set up to be a breathing surface, an oxygen tank, all over the back of the animal. One of the things you need to work with the papillae, however, is the pedicellariae. And just FYI, the way these mini forklifts are oriented and designed is it's very similar to a fingerprint. It's how we're going to be able to tell different species. We look under a microscope, we see how the pedicellariae are set up, and that's going to determine what species we're looking at. Their overall function is to get rid of organisms, more than likely debris, though. You don't get one without the other. And the pedicellariae are vital for these animals' survival. Why would you need these structures set up, though, if you have this effective skin surface that's just constantly breathing for you? Why would you need these additions on there? Anybody got ideas?
Yeah, so actually you don't want things, you don't want to like breathe in dust or water or anything, not to anthropomorphize, but I'm speaking as a human. We because they breathe with their skin, quote unquote, they need some kind of like defense for their respiration organ, right? So these little crab claw figures, oh, I love that. I love them. And I just love this structure so much. Okay, so what they do is, because these these species, these organisms are benthic, and they're bottom dwellers, ocean floor, sand, everything. So these structures actually protect the organisms from free-floating larvae that might need a place to settle, to develop, such as the sea star and its stalk. It does need a place to settle and start developing. These pedicellariae act as kind of like a defense for those, as well as the sand when they're, you know, burying themselves in the substrate, etc. They also, so like the papillae also kind of shield the skin from the sand and acts as like a second skin as well. It just, overall, they just pluck things off of the organism or off of the starfish and keep it from, you know, becoming some kind of vessel for other beings to develop, but also it keeps the sand out of, you know, their breathing apparatus, etc.
That's, yeah. First off, that's fantastic, because I've never used that analogy of it's a defense mechanism, and that's exactly what it is. That's missile defense system right here. You're a benthic animal that's constantly being covered in both debris, falling particulates, things like that. This is your missile defense system that's set up to keep the respiratory organ, which is the entire aboral surface, clear and free of debris. Yeah, that's awesome. I never would have used the defense system analogy, but that's spot on what we're looking at here. Depending on the organism, they are going to be oriented differently. These basically just flop back and forth, picking up debris, but you can see how common they pop up. So there's one defense system for every sector of skin gill nearby. So they're all working in unison. Basically, what simpler models do, they'll pick up debris. So this folds over. Let's say here's some sand. This folds over, grabs the piece of sand, picks it up, holds it up like you're holding a dandelion in the wind, and allows the water to just carry it away. But it's keeping the respiratory organs basically free the whole time. Here are some other examples. If any of you are old enough to remember, a lot of these look like the movie Tremors, where those crazy worms come up from the subterranean depths. So the complexity of the Pedicellariae really do vary and serve as, again, kind of that fingerprint identification of, if we see this, we know what species we're looking at. It's very important for asteroid taxonomy and identifying what individuals we're discussing. All right, brace yourselves, kids. Here we go. We're getting into the water vascular system. I think personally, we've talked about a lot of cool animals with a lot of cool adaptations so far. This is right up there. This is an animal with no brain, no muscles, and is able to move and be arguably one of the most efficient predators out there. I realize they don't have their own Shark Week. You don't see Nat Geo advertising like a lion taking down a gazelle and then an asteroid taking down a mollusk. It doesn't get the hype tape associated with it, but when you find out how they're able to use their own environment, it's pretty impressive. So the beginning of the water vascular system all starts with what we call the madreporite. This is a sieved plate. It's a bunch of calcium carbonate assembled into one, I want to say like a colander, like a cheesecloth, if that makes sense. So it's very porous for water to move, but no solids. It's like a cheesecloth inside of a colander. You're able to move water in, keep all the external solids or maybe substrate, things like that, keep it all out of the water vascular system, and just allow pure water to flow in. This is the start of the water vascular system. Again, most of the time, not you all, because you're in zoo classes, But if you asked the general populace, most people would probably say this right here is the anus. Um, that makes sense, I guess. It's an external opening. It is not. It's the madreporite. It's the start of how they move and eventually acquire food, as we'll discuss. But madreporite super important. Anus is usually located almost right above the oral surface. So oral down here. This is the aboral, the top side. Again, we have to use these terms now because we're dealing with a dorsal ventrally flattened animal. But ventral, underside, dorsal, top side, aboral or oral are the same thing when we're talking about sea stars. Sorry for all the arrows. The water vascular system itself is going to be used for almost every element of these animals' lives. Extremely important. The method in which it's deployed is so it's smart. It's efficient. It blows like whatever we're trying to do right now as far as electric cars and green energy. It blows it away. This would be like your car running off sunshine and wishes. You're just using whatever's in the environment around you to do everything. You're going to be able to move. You're going to be able to acquire food. This is like Uber Eats with no delivery fee, I guess. You're using the existing environment and conducting all sorts of behavior, food acquisitions, and locomotions at virtually no expense to the animal. We talk about, if you guys have taken reptiles and amphibians, for example, being animals that use that external heat source, an endotherm versus an ectotherm. Being able to use the sun is very effective. Being able to just use the environment which surrounds you constantly with water, that, pun intended, I guess, blows it out of the water as far as the effectiveness that these animals are able to exhibit, despite the fact that they don't get that much credit. The water vascular system is really easy to talk about in sea stars because it makes sense. We can visually observe it, we can look at it, and see what's going on. Where it does get a little tricky is when we move into different animals. So at the top right of your screen, that's how we're going to discuss the water vascular system because it's a very easy visual. At the bottom, though, we've got holothurans and echinoidea, sea urchins and sea cucumbers, both of which have some really unique properties, but still operate in that same water vascular system model. Yeah, I think to highlight, I guess, these two species, does anybody want to chime in on either urchins or cucumbers?
Yeah, so if I may, uh, the sea cucumber is quite the creature. It's, as you can see, its respiratory tree is stemming from uh its posterior posterior end. So its cloaca. Uh, Actually, a lot happens with the sea cucumber's cloaca, if I may. Um, So they have a cloaca. If you're unfamiliar with the term cloaca, it is a term for one hole with many purposes, typically found in birds, reptiles, amphibians, just to name a few of those who have a cloaca in the animal kingdom. So it's used for an all-intensive exit region for eggs, or even an entrance region for, gametes. Also exit region for solid waste and urates, especially in those listed animals, since they don't urinate, they're just urates. Anywho, I'm digressing. So it is always just a single multi-purpose opening at the posterior region of an individual. The sea cucumber, though, I don't know if it knows about that kind of quote unquote rule, because the sea cucumber like I said, like you can see here, the respiratory tree kind of links in with the cloaca, and the cloaca, which is the little purple doodad at the end of up at the right side. I'm sorry, you can't see my mouse, so I'm just trying to describe. Thank you so much, Alex. That is the
Of course.
cloaca in which it breathes from. If you want to get technical, they breathe from their butts. But it's not a butt because it's a cloaca. Anyways, not only that, if debris gets sucked in there, because I don't know if you guys know about this, but sea cucumbers have the same feeding method as earthworms. They just suck up everything, specifically sand, debris, substrate of whatever it's swimming through and crawling against, and it's filtering out the nutrients through that, and then just basically poops out sand, but through its cloaca. But it also if debris gets sucked in during respiration, it will digest any nutrient properties, organic matter, through its anus, if you will. And there's also a little fun symbiotic relationship that it has with two animals that I can think of, but possibly more if animals start realizing they can exploit this feature. So there is a crab called the harlequin crab that will live on or within the cloacal area of the sea cucumber, but I really want to just put a spotlight on the pearlfish, because pearlfish are they're a special breed. They like to exploit the sea cucumber's body cavity for a home, but there are like parasitic, and then there's commensal relationships going on there. So the parasitic ones, they'll make a home inside the sea cucumber, but they'll actually start eating away at the sea cucumber's reproductive organs slash innards. But then there's another species, or there's other species of pearlfish. They're kind of considered anquilines. I came across that term. It just basically means an organism that utilizes another organism for a safe place or a place to live. But yeah, that's where the commensal symbiotic relationship comes in. They kind of keep the sea cucumber safe from, well, or maybe they're just utilizing the sea cucumber's cavity space inside their cloaca. But yeah, so basically this fish lives inside the sea cucumber's butt, and it can either be parasitic, or it can, kind of, it just benefits from anything that's passing by the sea cucumber for food and safety. So there's that.
Yeah, and sorry, kids, but that's exactly right. Like, it's weird to say, and it brings out that, I think, inner child in all of us of saying, like, oh, it breathes through its butt and a fish lives there, but that's exactly what happens. And I'm so glad the pearlfish was brought up. What a cool, weird, like, I don't think anything highlights the invertebrate world more than that. We don't typically see that in that easy little babble bubble of a symbiotic relationship where something lives in literally your butt cavity. At least, hopefully, that doesn't come up with mammals too often. But yeah, they're breathing, they're using that cloaca and housing other vertebrate organisms at some point with the pearlfish, as opposed to the harlequin crabs or harlequin shrimp, which we'll talk about. Yeah, I mean, you're really, I think it went stated, that kind of one-stop shop, that one hole with multi-purposes. Now we've got another purpose, which is housing vertebrate fish. So yeah, very strange, weird animal. And again, we've got a tweaking of the respiratory tree, obviously using the cloaca as opposed to those dermal branchiae or skin gills, but still following the same WVS and 5-part body plan that we see exhibited. The other one's the sea urchin.
So the sea urchin actually has what's considered like a chewing organ, if you will. It's called the Aristotle's lantern, and it is going to be five. Sticking with our series of five. It's like five calcium carbonate, either almost like teeth or plates, and then it's kind of like a fleshy tongue in the middle, and then it's going to lead into like an esophagus and then a stomach. So they are kind of set apart in that they are going to like grasp and grind and almost, I mean, like chew what's going down compared to some of the others that we've talked about so far that are like starfish that are really just like pushing their stomach out. These guys actually have like full calcium carbonate hard grinding plates, and they are going like their teeth are going to point inward so that they can grab things and kind of trap them in there, to help with that, like them not just escaping the teeth. Like I yeah, point inward. I can't really describe it without trying to draw it, and you can't see my mouse.
Yeah, that is hands down the unique qualifying trait that separates Echinoidea, the urchins, apart. And I'm super jealous that somebody else got to say Aristotle's lantern. So I'm going to say it, Aristotle's lantern. It's one of my favorite zoological terms. I think it's just awesome. It has a cool ring to it. But really actually does serve a very vital function for urchins that does help set them apart and gives them some feeding advantages, despite the fact they lack the obvious, at the top right of your screen, obvious five rays in order to manipulate prey. Aristotle's lantern kicks in and serves arguably a more efficient function. And while both explanations of these animals are completely accurate, uh, the thing I just want to reiterate and highlight is all of this is powered by water. It's literally done with the environment around you. There's little to no actual muscular contraction. All of this from the crazy respiratory tree that we have with sea cucumbers, to Aristotle's lantern, to movement, the orientation of the spines, the auto evisceration, all of it brought to you by the ocean. Um, Extremely efficient animals. When you consider both the speeches we just heard on both these animals, both pretty impressive. I think it gets like an extra boost up when you consider the fact that, uh, again, this would be like your car running off your good thoughts. You're using what's already around there, what surrounds you completely in your environment, what envelops you, and using that to perform all of your tasks for the day. This is like a Roomba that never needs to charge. It's running, performing tasks on a daily basis, but doesn't need an external energy source. It's literally surrounding you all the time. So, excellent explanations of both animals. Aristotle's lantern. There, I just wanted to say it again. I think it's one of the coolest terms out there. But really cool properties, all powered by the water, which lets us dive into now the rest of the water vascular system. So I'm going to tell you guys real quick the very long, drawn out explanation. First, though, to summarize, let's do the easy one. Water comes in through that madreporoid, that sieved cheesecloth calcium carbonate plate on the ab-oral surface. Water goes into the animal, it gets pushed through the animal, and then pushed into what we call the tube feed. Please note, for testing purposes, tube feed is a combination of this and this. Tube feet is not a relevant term. We call them tube feet, but we're talking about two very specific individual parts. So you can associate them in your head as two tube feet, but we got to understand the functions and the purpose of each of these being labeled independently of one another. So in an easy version, you bring water into the animal and then extend these tube feet, that moves you forward. Or you contract the tube feet, that brings you either adhering or staying put, latching on, or possibly prying apart prey. That's the easy version. Nobody, to my knowledge, up till now has come up with a cool song for this, like the knee bone connects to the hip bone, like whatever. If any of you want to come up with a new song, be greatly appreciated. But here's how we're going to follow the flow of everything. Madreporite starts all of it off. Again, that's our colander at top. Water enters. It's going to enter the stone canal. And don't worry, there's visual for all this, but we're going through the text right now. Water's going to enter through the stone canal. The stone canal's one of the only solid pieces of a sea star. Again, we talked about that imagery of kind of chain link where bend but not break. This one's pretty solid. The stone canals, I guess a good analogy would be like an old brick chimney, where instead of smoke going out, oxygen's coming in, if that makes sense as far as imagery goes. We've got the madreporite and then a calcium carbonate laden, stiff and rigid chimney that goes down and feeds the rest of the ring canal. So our stone canal is the only solid connecting point. In the before times when we could do dissections, this is what we typically do. You take, I'll do a virtual dissection right now. Here's a sea star, perfectly proportioned. Here's the madreporite. What you do is typically, I'll use a different color for the dissection portion. We're going to remove the skin here and peel back everything and work our way towards the madreporite. The madreporite, again, connecting that stone canal, this is the only solid part. It's going to connect to the ring canal. So madreporite sits here. We work our way back in this virtual dissection that I'm doing today. Work our way back towards it. And you can literally, if you take a probe, I mean, you can tap on it just like that. You can tell you've hit, again, kind of that stone chimney, I guess is a good analogy. You can tap against that stone canal and feel the rigidity of it and the strength of it. Its purpose is so vital. It has to be the solid part of the sea star because it feeds all the rest of the water vascular system. That's the connection point. That's what gets you from point A, madreporite, to point B, ring canal. That's the stone canal's job. The ring canal, just like it sounds, it basically, oops, excuse me, guys, basically sits around that central axis. So sea stars here, and that central disc that we see, the ring canals encapsulating all of that. From there, there's obviously 5 or more, usually multiples of 5, as was mentioned earlier. Multiples of 5, these are the radial canals. Oops. This is what stems off of that ring canal, and these feed each of the rays or the arms of the animal. Again, these are going to sit above that umbilical groove. So follow me here for a second. We've got our dried up sea star from the gift shop. We're looking at the underside of it. We see that umbilical groove. Again, almost like an aqueduct, but it's a rigid calcium carbonate bridge on top of which sits these radial canals. They're going to start feeding these, again, tube feet. It's the right term, but it doesn't clarify or exemplify the 2 individual parts of the tube feet. But the ring canal is going to extend out into these radial canals and feed the tube feet via the umbilical grooves. So this is why tube foot isn't the right word, because we've got 2 key terms here. The first term is podia. This is the terminal end, so the most distal end of the animal. Again, I've got visuals, but perspective-wise, this would be, I guess, like your fingernails. That's the distal end of your fingers. And the podia's job is very simple. It either adheres or doesn't. You either grasp onto something, and again, picture like the suction cups that you see the spies using in the movies where they climb glass. Um, you're either turning on the suction or not. That's its only purpose. And the one doing all the work is the proximal or closer to the animal. It's a accordion-like contraption. The ampulla. The ampulla is the one that's really going to give this animal everything it's able to utilize. With the ampulla, the power exerted is very impressive, especially again considering the fact that we're not using any muscles whatsoever. I think that makes it all the more highlightable. It works like this, and again, picture the ampulla working kind of like an accordion. If I want to move forward, my distal ray that's moving, let's say we're moving towards light because we're going to incorporate everything here. We're exhibiting positive phototaxis. I want to move towards the light. My ray reaches out. The podia is going to adhere to the substrate or the surface in front of me. And then my ampulla, the accordion part of the leg, that's going to suck water out and contract, therefore drawing me closer. Meanwhile, on the backside of my body, I've got podia that were adhered to a substrate, have now let go, and the ampulla are going to fill with water and extend and push off. Does that make sense to everybody? We want to adhere and contract. That moves us forward. On the backside, we're disengaging and expanding the ampulla. So hopefully that makes sense as far as the real breakdown of how these animals move. But this also works for food. The feeding process to, like, let's say, pry open a bivalve consists of all of the podia adhering to the bivalve, both sides, and then all of the ampulla contract and draw the water out. And you're basically slowly, very slowly, prying open this bivalve prey. It's slow, but you can't really knock it since you're exerting literally no muscle effort whatsoever. You're just using the ocean and drawing water out of your body. This would be like the equivalent of going to the gym and working out for 17 days straight, but using no muscle contraction to actually lift the dumbbell. You're just using the gross, sweaty air of the gym. It's slow, but man, it's hard to argue that you could find a more effective animal in the realm in which these animals live. And just to point out, and we're going to talk about it shortly, the other thing I want to point out too with this act of prying open a bivalve is the whole time the bivalve is using its own muscles to try to stay closed. So you've got, it's like arm wrestling, like a professional arm wrestler, and you have no training whatsoever. You're going to be struggling the whole time, whereas this almost muscular but no muscles wrestlers coming in and can just dominate the field. They just don't care how long it takes. You've got an animal that's working, flexing every bicep, if you will, the adductor muscle, trying to stay closed. And you've got an opponent who doesn't care how long the outcome takes and isn't using any muscular effort whatsoever. They just have to wait you out. They're going to wear down that adductor muscle eventually. So very, very efficient in that regard. So here's the visual that goes with all the text we just talked about. The B right here, that's the stone canal I was telling you about. That's really the only rigid, true, sturdy part of the sea star. The rest is all designed for flexibility. So madreporite, stone canal, again, madreporite connects to the stone canal connects to the ring canal. From there, everything extends out and goes to the radial. The ampullae are, again, the accordion part of the legs, and F here is our podia. They kind of look like roast chicken drumsticks on your screen, but this exact diagram is going to show up exactly like this on your exams. So make sure you either you can screenshot it like this, or it'll be uploaded to your D2L. Either way, whatever helps you study the best. It'll be this exact image. And yeah, just please don't call them tube feet unless you understand that you're identifying two different structures, the ampullae and the podia. Both different structures, both different functions. The image right here, I think, is one of the better examples of how these animals would work. You can see very clearly a color delineation between the podia itself and the ampulla, where again, just kind of slow motion it in your mind and think about the exact process that's occurring. If this adheres to something and this expands or contracts, you're moving towards or away from something. If everything here is adhering and then you just retract the water from your body, all those ampulla are pulling back. The podia's only job is to adhere or not adhere. It's almost a very thoughtful process, despite these animals not having the brain in place to carry out that thought process. But very, it's very designated, everything's role. I guess that's a okay way to say it. It's very purposeful with how these animals move, operate, and acquire their prey species. And let's be honest, I'm talking to a group of zoo kids. Your knowledge of automotives may not be vast. Think about this though, like air intakes. For an engine to run properly, the more powerful that engine becomes, we're going to need more air intakes or more oxygen flowing in. Same concept here if we consider the sea star an engine. As the animal develops more rays and a larger body plan, again, here's another sun star, we're going to develop more madreporites to feed that ring canal and the radial canals. There's not a general consensus out there of like for every time you get 5 limbs. So let's say your standard sea star has 5. This species has 10. It doesn't necessarily mean you get a new madreporite every 5, but for the sake of today's lecture, I think that's a okay rule to go off of. If I've got this enormous central disc now, and I'm feeding all of these rays with their associated tube feet, ampulla, and podia, I'm going to need a madreporite here, 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 and here. Let's just say. I'm going to develop more madreporites to get more water or more oxygen intake into the engine that is the animal. The rest of the system remains the same. Does that make sense? So I've got the ring canal. That's this line right here. That's your ring canal. That's always going to stay there. It's always going to feed the radial canals. Always. We're not getting more rings or more radials. The only thing we're doing is getting more madreporites in order to better fuel the engine and give it more gas when it really needs it. So more madreporites, it does mean more stone canals. Everything else remains the same. I've created new opportunities for water to enter the body, and that helps power the 50 legs I have now. But after madreporite stone canal attaching to the ring, that's it. Everything else is the exact same across the board. So with this model, and again, I know I've harped on it a bunch, but sea stars have been very efficient. They've done a great job. And again, they're that almost evolutionary link with that deuterostome development between that transition to really vertebrate life. Uh, Evolution would dictate that they're technically our closest invertebrate ancestors until we get to hagfish. We'll talk about them. Nobody has a picture of a hagfish on in their family photo albums, but they're in there too. But invertebrate wise, they've been doing it well for a long time. They're very well represented across the world, definitely stemming into the Arctics, which is unheard of for a lot of ocean dwelling species. Very, very prevalent, occasionally teetering on the edge of invasive. But we have a unique history with them, to say the least. Our involvement with these animals has changed and dictated the course in which these animals would wind up thriving in. And really, it's kind of one of those time to look in the mirror, kids. Only yourself to blame. It starts with the Northern Pacific sea star. It typically or normally would have inhabited New Zealand and Australia, but eventually gets transferred mainly in larvae or embryonic form via boat ballasts. And humans being humans, we did the most human thing ever. Decided to ramp up an initiative to remove these invasive species. It didn't work out great. I don't know. To elaborate, does anybody have any idea what happened with the Northern Pacific Sea Star?
I sure do. Because the Northern Pacific Sea Star was hurting the shellfish industry, fishermen were cutting them into pieces and throwing them back. Just throwing them back overboard, let the seagulls eat them or fish, whatever, free fish food. What had happened was parts of the pieces that they had cut, like, cutting them in half or just like dicing them and throwing them back, whatever pieces had a piece of just a skosh even of that centralized disc, grew a whole new starfish. So what they had done was, at the very least, doubled the starfish population. So they basically kind of dug themselves deeper, in a sense, by cutting them in half.
I mean, bravo. It's the most human thing ever. Uh, and what was really funny with this whole process of deciding to eliminate an invasive species by cutting them in half, let's go back to slide 2 or whatever it was. One of their most notable traits is their regenerative abilities. Shy of that, we also paid these people a ton of money. The US government shelled out tons of bucks for fishermen to go out, chop sea stars in half, double, quadruple, quintuple the population, thinking they were doing the right thing. And then as time progressed, fishermen were hauling in sea stars that were now starting to regrow these limbs and saying, that's weird. This animal looks like it was chopped in half. And then a few eyebrows raised, a few light bulbs came on. And yeah, I mean, I think it's one of the most hilarious, iconic humans thinking they can control nature type stories out there. To try to combat an invasive species, and the only thing you did was magnify and exemplify the population tenfold, and get paid to do it. Like, it's a dream job, guys. And we were responsible for all of it. It has nothing to do with the fact that, yes, these sea stars are very dominant and very invasive, but they're invasive because of us. They didn't come knocking on the Atlantic coast of America and then working their way to California and knocking on that door too. We brought them, then we chopped them in half to give them more opportunities to breed and quadruple their species. It's just one of those, like, yeah, I got you, humans. I know how you guys roll. It's a very human element associated with all these animals. Talking about how invasive and how devastating they have been to our ecosystems, though. And there it is at the bottom. It's actually very common in the pet trade. Obviously, they're very hardy, very invasive, so very easy to capture and breed in captivity. But on the invasive side of things, it brings us to what we call the ISSG. This is, I feel like, one of those I wish that got talked about more, maybe in like intro to zoo or conservation. Um, Everybody, for the most part, is familiar with your SSPs, right? Um, the Species Survival Plan, the IUCN Red List, so endangered animals. Everybody's familiar with those terms. Part of what the IUCN does is publish the ISSG, the Invasive Species Specialist Group. It's a mouthful, but it's cool. And they do it in a really unique way, at least in the past. Uh, this is probably 5 years ago now, had cool kind of comical profiles for these animals, of almost like America's Most Wanted type thing, like a wanted poster, uh, and had kind of funny descriptions uh, to highlight the ways that these animals were taking over their ecosystems. As fun as they tried to make it, a lot of people don't even know the ISSG exists. And again, it falls under IUCN, which is something you guys all should be familiar with. Um, so it's a well-respected list of major offenders. Um, there's the North Pacific Sea Star, obviously, but there's a lot of other individuals that made their way onto the list. Anybody want to take a stab at what else is out there? What else could fall under the ISSG?
So this has always been one of my like, buckle up, kids, I'm gonna blow your mind. And then everyone does that like, oh man, we shouldn't have got her started eye roll thing. But like this list, man. Red-eared sliders, domestic house cats, bullfrogs, cane toads, rainbow trout, which is an awkward one. Like I got to researching all of this years ago, and now I'm like super fun at parties. Red fox, pigs, rabbits, goats, largemouth bass, oddly enough, gray squirrels, things like mice I can kind of see. And then my favorite currently is the zebra mussel, which fun enough is actually like, not to like veer too far off topic, but they're so invasive that they're popping up in moss balls, which are being sold in like aquarium stores and just like run of the mill, hey, throw this in your beta tank. And like zebra mussels are so invasive that they have made it into moss balls being sold to people's tanks, which is crazy. Super fun at parties. I digress. Continue.
Yeah,
Mercedes.
and that is a cool part of the ISSG. It does make you really fun at parties. Yeah, it's fun to list those off, but it is really cool to actually take a look at and see what's invasive.
Sorry, I was just gonna add to student two that, and I apologize for like just cutting in there. Zebra mussels are just so invasive that even in Colorado, if you go up to Pikes Peak and start kind of divvying around the reservoirs, there's signs that say like, do not put XYZ because of zebra mussels into the water. And it's zebra mussels are typically an issue with lakes, not only because of transporting with boats and stuff, but river, veining into lakes from the ocean, etc. It's just crazy that invasive species anywhere, any species, it's there's still disclaimers in places that even though you really shouldn't have to worry about that kind of stuff. In the middle of the country where there's not really any rivers or waterways going to this reservoir, there's a big sign that says, hey, just be careful and don't put XYZs into this area because of these invasive species. Same with starfish. Again, with the whole, chopping them up thing as well.
Yeah, that's, I think, a very magnified look at what we're doing to ecosystems. As was said, like Zebra mussels are popping up in places they shouldn't. Areas where there's not a concise connection with the waterways. And then, as was brought up too, yeah, this is like very relevant, up to date news. Uh, they've just found zebra mussels on the little moss balls that you're supposed to put in your betta tank. Like, if that doesn't show you how effective and invasive an animal is, I don't know what does. It's made its way onto like the production line. Um, that means you're harvesting, growing, selling to a pet store, and meanwhile, this invasive little hitchhiker has gotten onto the assembly line. Um, Extremely effective, and without digressing and going down a crazy rabbit hole of ISSG stuff. Um, I love the examples that were brought up. Cane toads, one of my favorites. Uh, Cane toads were literally introduced by humans to combat another invasive, what we thought was an invasive species at the time, and now cane toads run the world. Bullfrogs. One I do want to highlight is the red-eared slider. That one's huge, especially I think it hits home a little bit more here in Colorado. Uh, Red-eared sliders look a lot like our state reptile, which is the painted turtle. Um, they look pretty similar, but outcompete them in every single way. They're more voracious, better appetites, uh, more aggressive. Uh, just in every way, they dominate the sport of being an aquatic turtle in Colorado. And what do? We sell them nonstop at pet stores. If you guys check the Humane Society website, I guarantee they have red-eared sliders right now. They always do. People, they're like a revolving door. People adopt them, think they're cute, realize they're disgusting, redonate them. They get to adopt them out again. And then the people that don't want to donate them dump them into the lakes. And then from there, they just perpetuate a invasive species stereotype of being completely dominant and ruling everything. So very frustrating. The ISSG is definitely something I would check out, though. It's cool to stay up to date. And again, I'm so glad that everybody brought up kind of the main offenders. Zebra mussels being really high on the list. Red-eared sliders. The rodent quota there is kind of understandable. Rodents kind of follow us around, so we've perpetuated that as well. I guess the big thing I want everybody to look into, if you do investigate the ISSG further, is how many of these invasive species are quite literally because we've introduced them to that environment. Nature has a pretty good checks and balances system of not letting anything get too far ahead in the race. We're the ones that have altered it. There's very few species out there that just decided I'm going to take over everything. It's usually, hey, we're good where we're at. We're going to stay here. And then humans distribute them across the world. And they're like, well, we'll just set up shop here too. So always interesting to see all the wonders we've done for the natural world. And I'm not going to go too far into this. I'll save this for Geneva and Bird's class. But I think one of the oddest things on the list that most people don't consider very often is your domestic cat population. They are decimating songbirds by the hundreds, thousands, millions. Arguably one of the, I guess, cutest to most of you. Everybody thinks invasive species are always these disgusting, warty toad monsters. Nope. Domestic cats. Your cats that you let run around in the yard and then went off and breed, have babies. Those species grow up feral and monstrous and just eat every songbird ever to migrate through Colorado. And again, believe me, much bigger than Colorado. But we have a huge problem with it here. Yeah, just I think it's something to look into. I think it's worth investing a little bit of your time, especially since most of you are familiar with the IUCN. Check out the ISSG too, and realize what is around you and what we've done to the world. It's if you go too far down the rabbit hole, you might just shake your head and give up on it. So don't go that far. Go just far enough to be conscious of what we're doing, both in the pet trade and the captive bred animal species that we seem to think we have a control over. So, awesome sidetracks aside, back to the functionality of the sea stars. You got to assume these animals inhabit almost every ecosystem imaginable. And the most notable one on here is again, that intertidal zone. That's an area that's really hard for animals to manage. You got to figure you rely on water to move. So when a wave crashes in, you've got to absorb enough water that you can still move around. But you're also willing to risk the added benefits of everything that washes to shore, the things you can eat, and be able to function from that standpoint without the reliance on water 24/7. So every imaginable habitat these animals are thriving in. The flexibility, as I mentioned earlier, extremely important. And I know it sounds weird to say, but it's probably their greatest quality. It's rigidity and flexibility all tied into one. I think, again, the kind of chain link or chainmail armor is a great analogy because you've got this structure, but it's so flexible across the board. You can adhere to a rock with waves crashing in. You can stay adhered to that rock. You can use the water to move away or disengage from that rock. Meanwhile, putting up with crazy tides, the environmental forces around you, really do kind of give a testament to how efficient these animals are. It was mentioned a bit ago when we were talking about taxus. The true brain isn't there, but there is a CNS or a complex nervous system. It basically follows the exact path that the water vascular system does. So it extends down those radial canals, centralizes on that ring canal. So there's a nervous system in place. There's, again, just not the motherboard to assign tasks or to send out a message. Everything just kind of works on its own and kind of high fives and teams up in order to accomplish a task, but there's nothing giving out the orders. With how this affects you husbandry wise and caring for these animals, it does mean that you can, it's weird to say, train echinoderms, and you can. It's a lot more conditioning or stationing, and obviously because these animals don't particularly like a head scratch or a scratch behind the ear, it's usually going to be very food motivated. But you can condition them to usually move to a part of the tank for feeding purposes. And this actually is really useful when you're talking about keeping an animal like this in captivity, where you want it to be on display for guests, not adhered to the back of a tank or the back of a rock somewhere, smashed in between two outcroppings. Nice to be able to know that you can bring them to the front where guests can engage them, possibly even see their feeding behavior, which is more complex than we've probably led on so far. We are going to talk about the modalities in which these animals are able to eat, but conditioning wise, you can train and work with these animals. It's not fast. It's not super exciting. You're going to need a very long, Facebook live stream to capture all this action, but you can do conditioning and behavioral responses with these animals. Again, everything's going to kind of follow that idea of the water vascular system. It's going to follow that model. Again, running along the radial, meeting at the umbilical grooves, and then the central disc afterwards. The way the animal functions, again, without that motherboard sending off a signal. Here's a fun task to do at home, kids. if you look at something in whatever room you're in right now, that's probably 10, 15 feet away is a good way to probably gauge it. So 10 or 15 feet away from you, look at a small object, and then you put your thumb up and try to cover that object. Using both eyes, you hopefully semi-successfully covered that object. And then if you alternate closing your eyes between right and left, you'll find that one image has your thumb pretty much over the item you were trying to cover, and one image, it's way off. That's because you have a dominant eye. It's the same. You could also do all sorts of cool stuff during this online teaching time. Do cool stuff at home like this. If you stand still, take a step forward, that's more than likely your dominant side. You'll probably start walking with your dominant side foot. Same way if you right or left-handed, usually your feet and your eyes follow in that pattern. Again, if you're left-handed, you'll probably take a step forward with your left foot and probably see more dominantly with your left eye. With asteroids, because we have 5 parts, we're going to never have a dominant anything. It doesn't make sense. That'd be too much conflict. What winds up being dominant is whichever ray detects the stimuli first and strongest. So let's use phototaxis for the time being, the movement towards or away from light. If the animal, and again, remember light means depth in this situation. If an animal wants to move towards the light, let's say it's breeding time, we want to go more intertidal / low bodies of water. So I want to move towards the light. Whichever of my 5 rays detects the most light kind of takes over. And it almost drags the rest of the animal with it. The other limbs respond, but the dominant ray is whatever has detected the stimuli and responds to it the best. So let's say my upper left, because I have 5 rays now, upper left has detected light. That is going to start crawling towards it. The other rays are basically to push to aid that limb. So when you see sea stars moving, they'll more often than not be, and I don't know a better visual aid than to just describe it as dragging the rest of the body. You'll see one ray very purposefully headed towards a stimuli, and it does look like the rest of the body's kind of trying to catch up or just help out. Like, hey, we know what you want. We'll help you get there. But you can visually observe one ray being very dominant, headed towards the stimuli they want. And the same goes for chemosensory functions too. So detecting usually an ammonious compound, but an animal nearby that could be a prey item, you'll see that ray take off towards that. And then in the meantime, you do still have these other 4 out of the 5, 4 rays picking up their own chemical or light cues, things like that. So just because one ray heads off in the right direction, I've still got 4 compasses almost that can at any time pick up the stimuli a little better. Maybe I've gone too far left and one tells me, hey, now it's right. That ray takes over. So a lot more than meets the eye when it comes to how these animals respond to stimuli and move around. There's a lot going on, and having 5 or more sensory organs, I guess, really does add a lot of complexity to how these animals are able to manipulate their environment and move around within it. With that behavior, it does lend itself to some behavioral adaptations that we've observed. We get what's called aggregations. Aggregates occur when multiple species show up. They are almost always followed up by spawning or breeding. So we've got a couple things that occur here. We'll start off with seasonal. Seasonal migrations, again, you're detecting day and night cycles. You're probably moving towards or away from light, meaning depth. There's a bunch of species that will venture into the depths of the ocean and basically hibernate during certain parts of the year. Usually, again, guys, I hope all this is tying in together. Light equals depth equals temperature. So light cycles are getting shorter, oceans getting colder, moving to a less lit environment means you're going down in depth, getting colder, getting ready to hibernate. All these things kind of compound and stack on one another. The spawning activity, this usually occurs in shallower waters. You got a picture of broadcast spawning here. And we'll talk about that again. I know we have before. The broadcast spawning that occurs makes sense if you're going to release just sperm and egg into the water to be in a very low water environment. You want to be in very shallow water. It doesn't make sense to go to the Mariana Trench and release sperm and egg and just hope for the best. You want a bunch of aggregate species compounding on one another. Everybody releases sperm and egg at the same time in a shallow body of water. It's like putting food coloring into a saucer filled with water versus a 75-gallon tank. It's much more effective in that smaller aqueous environment. And then the last one is feeding frenzies. Guys, like I said, it's not going to show up on Nat Geo anytime soon. There's not going to be Sea Star Week. The feeding frenzies that occur is, let's say, incident like whale fall happens, where you've got whale fall is the term applied to when a large-bodied organism sinks to the ocean floor. That ammonia output, the nitrogenous compounds of the animal being released into the water, causes a lot of sea stars to aggregate around them. They'll come in the droves, hundreds, thousands. It's a lot. They're able to very slowly process a ton of that food all the way down to the bone. And then usually, again, anytime we have these huge feeding events that occur that change ecosystems, usually ties with spawning activity or breeding. It's like a weird after Thanksgiving dinner orgy type thing, where all these animals have consumed copious amounts of food that they're not used to. That makes sense to ramp up the production of gametes and release those into the water. So anytime these animals aggregate, usually going to result in spawning at the end.
Hey, Alex,
Yes,
can I add a fun fact about sea cucumbers?
always.
So, not only do sea cucumbers not use their cloaca in a traditional manner, but if you ever, okay, I'm just gonna tell you guys, YouTube a sea cucumber releasing its gametes into the water. They rise up like a snake almost, so it looks like a little worm, and they release their gametes through their head. And there's like a little organ pore kind of thing up near their head, and I apologize for not knowing the terminology for it, but yeah, so they right up by their head, so they get up in a little almost column and then bend their head over, so almost like an S shape or like a little inchworm, and then they just release things into the air. And you said the food coloring, and I was like, and it does. It looks like right the first milliseconds that you put food coloring into a water, and it's like the string, and and I'm not trying to get all into it, I'm sorry, but like, it looks like it's releasing food coloring into the water right before it starts dispersing. It's super cool.
Yeah, you're absolutely right. And yeah, just hopefully you guys are enjoying talking about these animals. But yeah, you really, I promise you wouldn't waste your day if you did YouTube stuff like sea cucumbers. The symbiotic relationship with the fish that was mentioned earlier, super fascinating to actually watch, and the production and the release of gametes. And yeah, I know with this online teaching model, it's tough to get the visual, but yeah, that water food coloring, the way it disperses and radiates out, I don't know, just it's super fascinating. And I promise you wouldn't be wasting your day if after this you went and YouTubed a couple things and kind of dove down some very odd, albeit rabbit holes. Yeah, these animals, there's a lot more going on than meets the eye. We're going to go over this pretty quickly with the behavior of the animals. Tidal influence means lunar influence, so the moon, the sun, things like that. Again, light change. I hope you guys are compiling all this in your head. When we say that there's a pattern in activity based off light, again, light really means seasons. Light really means temperatures. Light really means depth. Um, there's so much more that goes on. Again, for an animal without that central motherboard making the decision for them, they can tell if there's X hours of light versus X hours of dark, what season we're in, when it's time to go breed, when it's time to go hibernate, when it's time to go into the ocean depths. I guess I can't stress enough the uh, volume of information that comes with every seemingly simple thing that's said. Uh, yes, they're behaving differently towards different amounts of light. But again, that means depth, seasons, temperature, tidal waves, lunar influence on those tides. There's, it's almost like everything's a loaded question or loaded term with all the caveats that they carry with them. With the, excuse me, feeding styles for these animals, they're going to be really vast. We've got, as was mentioned earlier, with the crown of thorns, and yes, we'll talk about them again and again and again. Crown of thorns specializing in coral. Many of these species specialize in eating bivalves. Some do algae. So there are some animals that are very honed in and locked in on one prey item. The chemical signals given off, again, I know it sounds weird and silly, guys, but we're outside of mammals now. It's not like a lion sniffing down where a gazelle is. You're in the water. The most obvious sensor to put out there is ammonious waste. So waste products. And again, these animals aren't necessarily urinating in the way you would think. You can put off ammonia or nitrogenous compounds just by breathing because you're transferring oxygen in, releasing CO2 and ammonia out. So just existing is giving off a chemical signal in the water. But we find this weird, maybe just a misnomer through the animal kingdom. I feel like so often when we talk about specialists, it sounds like a good quality as opposed to just a generalist. And that's not the case. Does anybody want to elaborate why the specialist part is much harder than being a generalist?
So when you're a specialist, like a habitat specialist or a food specialist, you are confined to wherever those resources are. When an organism is a food generalist, since we're talking about diet, um, this opens up it increases your fitness overall. The point I want to make is it increases your fitness. Now I'm going to explain. When you're a food generalist or a dietary generalist, what happens is you basically, the world is your buffet. I mean, obviously there's going to be things that an individual might not be able to eat or might, be too big or too predatory or unobtainable in some way, but you just have more options. It's almost like vegetarians or vegans are strictly no animal products at all, so they're limited to what they can consume. But someone or something that eats meat, animal products, eggs, vegetables, fruit, all of it, grains, everything, and they're not allergic to anything, that's a generalist, so they have more nutri you know it's easier to maintain their nutritional value versus an organism that is just specialized in one food item. And also, when you're a specialist, again, I mentioned you have to stay where the resources are, but then when those resources are depleted, then where do you go? What are you going to eat? And that's another way it kind of highlights that generalists can almost have an increased fitness in a sense. It's not saying that specialists don't. Um, Obviously, if other animals aren't eating their diet, maybe more for them, awesome. Maybe that will increase their populations. But generalists, just in a nutshell, have more variety of resources, and it's going to be easier for them to move around in a wider range of habitats and eat a wider variety of foods.
Yeah, wow, that was just wonderfully put. Yeah, I mean, I don't have much to add. I'm trying to get an analogy for it, but that was pretty spot on. The generalist lifestyle sounds so much more primitive, but does increase fitness typically. Um, Look at let's do a comparison between like the brown or black bears in Colorado versus panda bears. Uh, and we'll get into the bear stuff later. That's for mammals. I can do it because it's inverts. Uh, Pandas specialize not only in eating bamboo, but arguably the least nutritious species of bamboo. Like, they're, no offense if you love pandas, I'm sorry, but they're basically like dumb garbage animals. Like, why would you choose to eat arguably the least nutritious uh, local plant life when you could be like a brown bear or black bear that can knock over a trash can and eat McDonald's and styrofoam and berries, or a deer carcass? Like, the generalist model seems primitive, so much more effective. It's so much easier if the big thing, and it was highlighted in what was just said, is when things go wrong or things run out, you can move on from that. All pandas would die if that species of bamboo were to go extinct or they were to eat it all. Whereas, again, your black bear can just eat garbage from your trash can, go kill a deer. Like, you've got a lot of options. And this is a common theme I really want everybody to think about. Um, the more specific we get, yes, you're more efficient because you carved out a niche for yourself, but you have no flexibility when it comes to that niche. And here's a statement I always like to go back to. When we think about kind of the basis of this whole invertebrate theme, when we go back to coral reefs, which again are inhabited by sponges, coral, all the fish and invert species that live there, the sun, all the zooanthellae that coexist with them. Coral reefs are the most stable element on the planet. They're the most stable ecosystem and environment. And while that sounds good, it's not a good thing. That's why coral reefs are in such trouble, because the slightest change to that stable environment throws everything out of whack. Uh, and then you look again at, let's just take Colorado wildlife, for example, where you can have deer that live in the mountains or next door to you or are laying down in your yard, bears that either live in the mountains or eat your trash. Like, being stable only works if we keep that environment as such within those specifications. Um, and the slightest tilt throws everything awry, and can really mess with the chemistry and the alliance of all those organisms working together. So specialists, yeah, they're necessary out of trying to carve out that niche, but being a generalist is usually better. And again, if anybody listening is like on a vegetarian vegan diet, I'm not trying to change you towards being a generalist, but you do have that fallback plan of, if the store's out of asparagus, you can always eat a burger type thing if you're on that generalist side. So that's mainly what we're looking at. Sometimes stability is an ecosystem or an animal's worst enemy, because anything outside of stable can lead to death or significant decline in that ecosystem. So a couple of things we're going to talk about here, and we've hopefully built on all of this throughout the semester. The feeding styles, you guys know what a scavenger or detritivore is, something that kind of churns something back into the earth. The scavenger model is very popular amongst asteroids, eating dead or decaying organisms that have fallen to the bottom. Obviously, they're not free swimming, so they're not going to go actively predate free-swimming organisms in that pelagic environment. Suspension, excuse me, suspension feeding, and we talked about this with sponges, right? Suspension feeding versus filter feeding. Filter feeding means you're creating a conduit of water moving through you, a channel or movement of water, and then plucking out the organic particulates. With suspension feeding, it means that you're literally at the ocean's mercy, I guess. You're sitting there with your arms outstretched and grabbing stuff as it comes by, but you need the movement of water to occur for that the food particles to move by you. You're basically just, again, kind of sitting out there with the hands outstretched, hoping to get something. Very effective model. All your sea lilies do that, things like that. But reliant on ocean currents and the constant movement of water, which does happen all the time in the ocean, obviously. There's always going to be some debris passing by, but you're at the mercy of the movement of water and the microscopic particles within it. The one we haven't talked about, and this got brought up earlier, I think when we were talking holothurans, the sea cucumbers, and that's deposit feeding. Deposit feeding is super effective. With sea stars can cause some problems. Holothurans are much better at it because they have a more extended body cavity. And couldn't be more vital for our ecosystems to manage themselves. Deposit feeding is basically sucking up the substrate and the environment around you. You almost like a I don't know, like you see the assembly line workers that pick and pluck out things that either are defective or effective. So picture like your digestive tract's a bunch of Amazon assembly line workers picking out the right things. You're going to take out all the microscopic organisms and organic particulates, and then excrete all of the mud, dirt, sand, you name it. And it's a very effective feeding style, but it also is like vital for the environment. You got to picture all this organic particulate at the substrate of the ocean floor. Something needs to be down there churning through all of this, getting the organics out, consuming them. Otherwise, they're going to sit there and rot, decay, produce huge nitrogen spikes. So we need animals like this performing almost that earthworm niche, which I think was mentioned with the sea cucumbers. The downside of deposit feeding does kind of rear its ugly head when it comes to sea stars, because they're not the smartest. As far as the generalist side, as opposed to the specialist side, generalist means just that. You can eat algae. You can eat. You see here the sea stars consuming a deceased octopus. Octopus overall, they're food for a lot of species, but not a ton of nutritional value. So to be able to extract the nutrients that you need from this invertebrate animal, and again, another cool part of this kind of scavenger detritivore niche, because this animal doesn't have a skeleton, it will be turned into literally nothing. There will be nothing left. I guess a beak, which would be the only hard calcium carbonate part on a octopus body, but that's all that's going to be left. And of course, some calcium consuming algae or bacteria is going to grow on that. Maybe a crab comes along. Like you need these animals. They're like the people that come pick up your trash on Wednesdays. You need something there to churn all of this waste and turn it back into energy, both for the animal and turn it out of a detriment to that environment. With the feeding methods, this is where things can get a little bit interesting. Intraoral feeding is the easy one. We're going to start off there. This is where you go up, consume something. It's the equivalent of eating. Like, I don't know how else to describe it. It's just eating as you know it. In the safe mammal bubble, it's eating. This is where deposit feeding can get tricky. Because the animal doesn't have a brain, there's no system in place to say I'm full or stop eating. So, hypothetical situation with and Asteropectin's typically the species that exhibits this awful behavior. Uh, let's say we don't even have to go a whale. Let's just use a trout. Let's say a trout has fallen to the bottom of the bed. It's been decomposed, basically dissolved into the sand around it, or a tuna fish. Let's use tuna. Um, the Asteropectin and other deposit feeders are cruising along, consuming substrate, spitting out the actual sand deposits and keeping the organic particulates. All of a sudden, we stumble upon this area where a tuna has now dissolved into the sand. We engulf, take in a bunch of substrate. Almost all of it is organic particulate because it's all dissolved tuna now. And so we spit out nothing, right? Because we didn't really take any substrate on. I'll do it again because my brain isn't there to say, hey, you're full, you're good. And I'll take on another huge engulfment of organic particulate. And basically, they blow up or distend themselves and rupture their central disc. So they'll sever into two because they've taken on too much food from a really saturated organic particulate environment. So that is the one downside of not having a brain and being a deposit feeder. Asteropectin is arguably one of the most primitive sea stars out there. I'm not talking smack about Asteropectin, but not even amongst sea stars up there with the smartest of the sea stars. So it is a primitive model, and that's why, because it can really get you into trouble, and they rupture their central disc and die because they ate too much. The other type of eating here is extraoral feeding. This one goes a bit outside the box. The extraoral feeders are going to be able to exhibit a very unique characteristic when it comes to how they're able to feed. Here's some examples of extraoral feeding, but we're going to talk about it more in depth in just a second here. The extraoral feeding occurs by everting the stomach. So again, guys, and I know I mentioned it earlier, you got a picture of these animals clasped onto a bivalve. They're pulling them apart using no muscles of their own, and the bivalve is using every muscle it has to try to stay closed. And all we need is a 0.1 millimeter gap. That's nothing. That's the smallest like space imaginable to evert our stomachs. Evert is intentionally highlighted with an asterisk by it in this picture for a reason. Maybe have a guess at why evert is highlighted as opposed to invert?
So yeah, a lot of the time we think of invert, which would pretty much be like to turn it upside down or to just turn into like a contrary position, whereas evert is to turn inside out, like the same way you would like take your pocket and turn it inside out. So you're not just flipping it over, but it's like completely twisting upon itself and yeah, inside out.
Yeah, exactly. I'm glad the pocket analogy was used. That's perfect. It's the idea of if you had 50 cents worth of change in your pockets, I could invert you, which means turn you upside down and change would fall out. Or I could tell you to evert your pockets, which would mean you pull your pockets inside out and the change would fall out. But huge difference. Invert is not the right term to use. Please don't use that on your exams or terminology going forward. Everting is what the animal is able to do. The stomach itself is everted from the mouth and brought into contact with the bivalve prey, usually, that these animals are trying to consume. One of the interesting things with this is the animal is able to use the bivalve shell almost against itself. hang on, let me go to the next slide. The process is very slow, but follow me here for the imagery, and we're gonna see it in just a second. Uh, if you're going to evert your stomach, uh, meaning put the stomach outside of the body, it's going to release all the digestive juices that a stomach normally would. Uh, we need the animal shell present. So let's look here at this bivalve being consumed right here. We need that shell encapsulating all of those digestive processes that are occurring. We need that shell there. Otherwise, just putting out digestive juices or bile, if you will, out into the ocean, that's just going to float right away. Like you're not going to accomplish anything. So we're going to use the animal shell, almost like a pot with a lid on it, uh, to encapsulate this digestive process. We'll be able to evert the stomach, go into the animal's home, habitat, shell, um, release digestive juices, absorb those juices back through the stomach, and then walk away, crawl away, unscathed and fuller from the process that took us literally no energy for the most part, no musculature was exerted, but we've overpowered an animal whose entire evolutionary history dictates grow this huge muscle to stay shut, and we've outsmarted the system using the aqueous environment around us. Let me see if this will pull up, guys. All right, so a couple things I want to talk about in this video as it's going. You can see the dominance of the rays that are picking up different signals. You can see one ray that clearly has figured something out and is on to something. It's like a bloodhound that's got the clue. It's leading the way. Everything else is helping. But as you get closer, the directionality is going to shift as to what rays are moving. Great image right there with that dominant ray moving forward. Everything's reaching out. And then this is the image I wanted to get to. Don't ask me how they got like a little GoPro camera inside of a bivalve, but here we have the podia and the ampulla working together to separate the animal. And here at the middle of your screen comes that everted stomach. And again, it's going to use the animal's shell almost against itself because it becomes the I guess pot with the lid on it. I think is still a good analogy. It encapsulates all those digestive juices uh, and the nutrients that the animal's going to absorb. Absorbing all the digesting and absorbing all the muscles in place. And then it's literally going to leave behind nothing but a shell of a bivalve behind. And it's used no energy on its own part, for, like generally speaking, absorbed a ton of energy, very efficient at bioconversion into biomass. So really efficient in that regard. The other species that exhibit this behavior really come into play here with the crown of thorns. And like I said, guys, it's no joke. They're going to pop up quite a bit. The way that they eat/destroy ecosystems is what we call patch digestion. So if you picture the video from before, we're using the bivalve shell in order to contain our digestive juices. When we have an animal that's built like this, however, where we've got this huge central disc, they basically, I don't know, if you guys have seen like a movie where they're trying to defuse a bomb or a grenade's going to go off, things like that, and you put the almost suction cup around it so that all the damage occurs within that sealed off area. Kind of the same concept, especially given how much damage these animals do. This entire central disc here basically adheres on to the coral. They evert the stomach and then process all both the organic compounds of the coral and any zooxanthellae living within them. And this part adheres, so we've got this like suction ring. The stomach's everted, juices are flowing, everything's horrible, and ecosystems crying. But the crown of thorns is very, very effective. You'll know as a marine biologist if you're entering an area where crown of thorns have recently decimated or knocked down that village, because you'll see that exact thing. You'll see basically a circular ring of white dead coral adhered to regular normal living coral, and it's because crown of thorns have been there, adhered themselves to the coral, and then patch digested what was underneath them. The rate at which these animals operate is astounding. It's significantly faster than corals can actually reproduce or grow. Which again, guys, by now should not be a shocker to you. With invasive species, yeah, they're good at what they do. It's always awful, but they're really good at it. So that brings us to what I think should hopefully be a callback for all of you, knowing what a keystone species is. But just in case you don't, let me introduce you to the OG of keystone species. It should be a term that a lot of you are familiar with. Hopefully in a little bit we can get some examples of other keystone species and what they represent. But the original keystone species gets coined in 1966 to describe a sea star. It's now moved on to represent a lot of other animals, but gets its origins with the humble sea star. And keystone species going forward, again, if you're not familiar with it, become familiar with it now. Has a lot of relevance in the zookeeping world. Does anybody want to expand on keystone species and what they really mean? Maybe some examples, things like that.
Yeah, so if we're talking keystone species within echinoderms, sea urchins can be considered keystone species because they eat algae, they actually kind of make a clean settlement area, especially after things like storms or coral bleachings. For new coral to the coral larva, or gametes, like to come in and settle and establish a new reef, as well as other individuals that need to anchor themselves to something to establish. But they can over clean, which isn't it's not good for any environment. They actually cause a little bit of harm, as much harm as they do good for coral specifically. Sea urchins do, because they can start kind of taking away that good bacteria and the good things that corals need to be able to thrive in a balanced ecosystem. But to counter that, because sea urchins can also be found in kelp fields where sea otters are also found. Sea otters are considered a keystone species to keep the sea urchins under control. So urchins can be considered a keystone, but they're also kind of not invasive, but kind of like a nuisance on the other side of the spectrum. But also other examples that you guys might be a little bit more familiar with would be like prairie dogs, grizzly bears, the orangutan, and even sharks. A fun one that I like to throw in there is the aardwolf, because I may have done a little bit of study on the aardwolf, but also they're more of an indicator species, but can be considered keystone because they their presence kind of tells farmers and also like just the population of humans or scientists in general like what the health of the ecosystem. So there's a lot of animals that are keystone species just by their presence. That have that duality of an indicator species. But yeah, I think everybody's mostly familiar with the gray wolf in Yellowstone, kind of changing the rivers, etc. Very so keystone species are species that really aid or boost the health of their environment, or somehow, even if you don't see it and it's not obvious, they keep things in balance, if that makes sense. Did I explain it okay?
Yeah, absolutely.
Like
Yeah,
if you
go
oh
ahead.
sorry. I was gonna say, if you were to take the keystone species out of their like an ecosystem, that ecosystem would completely change. And
Yes.
it's not necessarily that it would, I mean, I'm not gonna say it wouldn't get better, but it would most likely just become unbalanced.
Yeah, exactly. I think that hit the nail right on the head. They're shaping ecosystems. That's what keystone species do. Uh, and it's almost always, as was mentioned, gray wolves are a big one. Um, they're shaping it in more ways than you'd think of. And I also just have to stop and give a quick shout out to the lonely aardwolf, which doesn't get enough credit. I think that was an awesome pull because I have a special place in my heart for aardwolves. Um, but all that aside, like the keystone species shape their environment in more ways than just them existing. They, in the case of the sea star here, going to keep bivalve populations under control, take care of mussels which overfilter the environment and make it almost. It, it's twofold. When sea stars are taken out, bivalves run rampant. They overfilter the water and they can't move, so then they die. So we have a kind of a double whammy here. We have water that's inhospitable for any other organism to live in because all the nutrients have been filtered out. Then we have this enormous die off of mussels taking place. So now we've got a huge nitrogen spike. And without sea stars, that checks and balances is never uh, in place. It's never taken care of. And we found out that out the hard way by removing sea star populations and then having to reintroduce them because, oh man, yeah, they're actually running the show. They keep everything running. Mussels are going to do their thing. The ocean's going to do its thing. Nutrients are going to be hopefully prevalent as long as sea stars are there to keep that mussel population in check. Uh, like I said, guys, it should be more than a common occurrence by this time. Like nature has a pretty good system in place. The only time it seems to go awry is when we're intervening. Uh, Other than that, it seems to have things pretty figured out. Nothing's allowed to become a dominant species aside from us. Uh, Nature's greatest mistake. Um, but yeah, the keystone species idea and that term applies to a lot more. And there were some great examples brought up, but it it goes a lot further, I think, than most people give it credit for, even us in the zoo program, um, with what we think a keystone species really is and really represents. But uh, tip of the hat, it all starts here with a lowly invertebrate being the sea star, knocking off these mussel populations and realizing how a single species contributes and changes an entire ecosystem. The survival strategy for these animals uh, really kind of works against them. Uh, it's a great adaptation and evolutionary change that's occurred within these animals, but really serves to their detriment. They can go without food for a significant amount of time. Uh, you're talking a year or two without eating. And yeah, it just, for the hobby trade and the pet side of things, really does kind of serve to their detriment. With the feeding structure and behavior that you have to get down and work with these animals on, a lot of them are, just put bluntly, very cheap on the pet trade, so they're easily replaceable. Um, the idea that they have to actually be fed, usually target fed. Um, Target feeding comes into play a bunch, which people don't think about. Uh, these animals get lumped in very often with, oh, it'll just eat whatever's there or around. Um, does kind of lend itself to kind of these animals' downfall. Uh, Usually, they're dying very quickly in captivity, and again, quickly is a term used loosely based off the asteroid's ability to live so long without food. It's almost like a, let's go back to the sponge lecture. Um, when the sponge is exposed to air, yeah, you're going to have a sponge for a long time, but it's been dead from the second you put it in the tank. Same thing here. If you're not adequately target feeding or getting some behavioral changes down to make sure your animal's eating. The husbandry for these animals, more complex, I guess, than I think would be at the general glance. Uh, they're going to be bred quite a bit in the pet trade, especially, again, your invasive species. So North Pacific sea star is probably the most common sea star exhibited in both hobby and zoo displays because they are so virulent and easy to maintain. The flip side of it, occasionally sea stars are bred as feeders. Usually we think of feeders as that copious amount of little tiny goldfish at the pet store. Those are your feeder fish. There are animals in both the zoo trade and the hobby side of things that make their way into, I don't know, a relevant food source. It's a very unusual food source, but it still exists. And the harlequin shrimp is number one on that list. I think we talked about harlequin shrimp a little bit earlier. Uh, Harlequin shrimp uh, exist and thrive off of basically just the distal end of the sea star's rays. So the very tip of the arms. That's what they eat. The horror movie side of these, yeah, it gets weird, kids. Harlequin shrimp, if you want to keep them in captivity, you can. And again, please forgive how nonchalant I'm putting all this off as. Uh, they're invertebrates. This is what happens. Here's how it goes. A lot of the times, if you keep harlequin shrimp, you keep another tank with sea stars in it, uh, week at a time, sometimes twice a week. You'll go in, take a pair of kitchen shears, you snip off the tip of the asteroid's ray, and drop it in. The harlequin shrimp go nuts. That's what they eat. It sounds very morbid, but just wait, there's more. While it sounds a little morbid, harlequin shrimp are notorious for creating basically the most horrifying Saw movie type gardens. Basically, a pair of harlequin shrimp will team up. They will go out, find a sea star, bring it back to their creepy lair, put it upside down, so invert this time instead of evert. Invert the sea star so it can't right itself, and then they will literally sit there and snack on its rays, so the arms, um, And if that wasn't creepy enough, then they go out and collect food for the sea star. They'll come in and deposit it on the animal's mouth so that it eats. And again, without a brain, you're going to sit there and say, there's food, I should probably eat it. The animal eats while upside down in this creepy dungeon, uh, and is going to regrow the tips of their rays. So it's like a fully harvestable, sustainable, farm to table, creepy jigsaw version of a vegetable garden, where they imprison a sea star, feed it constantly so that it regrows its limbs, and then snack on them as their main source of subsistence. It's very weird, very creepy, very dark, but does hold the role as far as where sea stars are bred not just for display animals, but now for a food source. The idea that these animals are easy to keep uh, isn't necessarily accurate. They do come with a ton of challenges. One of the most notable is how, and again, it feels weird to. I have a soft spot in my heart for sea stars. Obviously, I think they're very cool, but the expense level of them in the pet trade, them being cheap, makes it easy to replace. That's just the cold hard truth of it. So many people, though, just like we talked about with sponges, are going to buy these animals and then assume that they're just great scavengers. They're going to eat whatever falls to the bottom of the floor here on this tank. I don't need to actually feed this animal. It's going to eat the waste that is produced in the tank. And there's a lot of animals that unfortunately fall into that niche. Uh, any idea of examples maybe that of other animals that fall into that pit of despair?
So really common when you're keeping fish, and we live in the wonderful world of Facebook. So a lot of Facebook groups you see like, why is my pleco dying? Cory catfish, loaches, a lot of like the shrimp that I used to keep all fall into this like, oh, but they're bottom feeders or they're waste feeders. People buy them to keep their tanks clean, and it's really simple though. Like now they make little algae wafers, and a lot of even just mainstream, like you can pick up at PetSmart, but even like throwing an algae wafer in there, um it's just stuff that pet stores should tell you, like, hey, your pleco needs an algae wafer every once in a while at the very least. Even though there are like a lot of natural things you can feed them as well, but they do fall in that people think they just eat poop and that'll keep their tank clean and that they'll be well fed, and it's not how it works.
Oh, thank you, man. I'm so glad plecos were brought up. Uh, Plecos maybe frustrate me even more than sea stars. It's the perfect example of this animal that people just assume like, oh, they eat waste. Like aside from dung beetles, there's not a lot of animals that just eat fish poop and call it a day. Like there's very few animals that feed on the waste of others. Uh, Plecos need their own, actually very specific diet. Algae wafers are a great mention there. I know for all my experience with them, and it's been years now. Uh, for me, one of the favorites seem to be sliced pieces of zucchini. They go crazy for that. Leafy greens, big part of their diet as well. They do incredibly well. They grow to incredible sizes. They live forever if cared for properly. But just like the sea star, they unfortunately kind of get lumped in with this idea of, oh, they're scavengers. They're going to eat the extra fish food that falls to the bottom, and that's definitely not the case. So yes, they're cheap. Yes, they're replaceable. That's their downfall. They can also live for 2 years without actually eating. But think about that from a keeper perspective. Like you've got an animal that you're exhibiting and either enjoying or profiting off of that you've never actually fed or cared for. Um, I realize there's not a lot of like signage out there and like nobody's protesting like, hey, feed your sea stars. I get it, uh, but is something to be conscious of. uh, if you go to a facility that maybe assumes that these animals are scavengers and just eating off the bottom, they do need a very specific diet regimented to them. And if provided that, are very effective at both living, displaying, behavioral conditioning, all that good stuff, if cared for properly. The other side of sea stars, a lot of people don't know how they breed. They're not super familiar with it. The methods of I guess the methods of displaying them sometimes fall into a bit of a trap themselves. A lot of people think that they are accessory animals, like they're just there to look cool. Cool, this thing has sea stars. A, half the time they eat coral. Uh, B, half the time they eat bivalves. So they're, and we've talked about this, guys, at length. The idea of something being reef safe. Nothing's reef safe. Everything lives in a reef to eat something else in that reef. And sea stars are no exception. Um, the flexibility, again, comes into play here. They are notorious for escaping. Again, there's no brain. They're going towards whatever stimuli they are interested in. It could be the heat of a filter running, could be the lamps, grow lights, things like that. And they are notorious for both escaping and then more importantly dying in the filters. This applies much more to the hobby side of things versus maybe a like a downtown aquarium type situation. But on the hobby side, they are notorious for making their way to the motor of the filter, getting stuck there or just wanting to remain there, and dying, and then basically just being a giant nitrogen bomb that produces waste coming out of your filter. It's the complete opposite of anything you want. So they do have challenges associated with them. Uh, and while I'm not saying like you have to put on your riot gear to go deal with these animals, uh, I just hope this highlights more. They're not just little accessory items. They're not decorations that go in your tank. There is a lot more that goes into both the care and the housing of these animals to care for them properly. Before that housing process takes place, we got to talk about QT or quarantine. Um, this is, I think, at least in my experience from both students, even people that work at the college, coming to me and asking me questions. QT is probably the hardest thing to explain uh, and to make relevant. Um, this is quarantine's like the equivalent of telling your kids to eat their vegetables because they'll grow big and strong. Like, yeah, it's true, but it's a real hard sell. And a lot of the times people overlook the importance of quarantine. Uh, Quarantine for possible contaminants is arguably the most important part of uh, an aquarist job. Um, Being able to identify maybe what you're even looking for, and then even the animal itself needs quarantine. Does anyone want to like elaborate or highlight or echo what I'm saying?
Yeah, so when you receive any type of organism, to add into your communal tank, your big picture show, you want to quarantine that individual first. I do not care if it's coral, sea stars, um, urchins, literally anything. Especially talking about the mossballs with the zebra mussels. I'm pretty sure the zebra mussels will like kill your, or will throw off your entire. It will throw off your entire everything, the salinity, your pH balance, everything, because zebra mussels just clean, clean, clean. They're another one that over cleans and just ruins the ecosystem that they inhabit. After doing some good, they just damage it all. But so anyways, totally digressing. When you quarantine, let's talk about sea stars. So quarantining an asteroid, you just received this specimen from 1,000% reputable, breeder or distributor, you know that they don't have any hitchhikers in any of their tanks, etc., you still quarantine it. And this is such an important yet intricate process in itself, because especially when you're working with animals that are sensitive to salinity changes, any of that pH balance stuff that you have to like make sure, like some animals are super hardy, some are super sensitive. Again, with the lifting a piece of coral from a tank and putting it into another tank, you've just killed that animal. I wouldn't even suggest doing that with well, anything. But fish are a little bit more hardier with that, but I personally wouldn't do it with a sea star. That being said, sea stars are very prone to they're just very sensitive to changes in salinity. So when you do that, when you start introducing it, you took the lid off of or opened a bag or however this animal came to you, you start doing what's called a drip acquisition. So the drip acquisition is where you take a dropper or just anything, and you're transporting drops of water in from your QT tank into the specimen, like where the specimen is already, and you just start dripping the water in there, probably once every hour for, I've seen where it's like 2 to 3, 3 to 5 hours, but you definitely want that individual to get used to the salinity that it's about to be living and breathing in, so to speak. So also the temperature. So you've seen where you put your fish bag in the tank that you're to kind of get used to the temperature as well. So once that drip acquisition process has, you're able to transition your animal into the quarantined tank, which you always need to do. I don't care what any online forums say, or if somebody says I didn't do it, mine are fine, you do it. Because there's always a risk, always. Even people who do all the tests, they still, you can always miss something, and you don't want to just like throw away like the whole aquarium that you're working at just because of a tiny something that you missed, and very potentially something microscopic. But anywho, after you've put it into the quarantine tank, you want to watch for physical or behavioral changes. This could be anything that you could see with your eye, like on the surface of your animal, white flaky things, or visible parasites, or swimmy, floaty, buggy kind of things. Also, if you're like where we're talking about sea stars, if it begins to curl, or it doesn't seem to be moving, like it hasn't moved maybe for the whole time you got it, and maybe it had a long trip to your house or your place of work, and you fed it and it's not eating, that's definitely a behavioral or physical thing. It might be dead. I mean, you just really got to pay attention to all of those things before you introduce this thing into your tank, or the habitat that it's about to be introduced into. And then I personally would recommend maybe even doing some kind of like another water change, or in that quarantine tank, just to kind of filter out, but everybody's kind of different with the way that they quarantine. As long as you quarantine, I would say even like 30 days, just so you have enough time to see what's going on with that animal, and then doing the drip acquisition into we're going to call it a communal tank, where you have everybody else waiting for their new neighbor. And once you've done that drip acquisition into that communal tank, you should be good to go.
Yeah, geez. I'm so glad this got brought up and it was explained. Like, I can't understate how important the part that was explained. Not only are you quarantining to root out any possible contaminants, things living with them, you're quarantining to acclimate your animal to that new environment. It's not just uh, picture like the old school movies of people going to jail or prison, and you have to get like uh, the delousing powder thrown on you, all that stuff. You're not just purifying your animals before they enter your enclosure. You're also acclimating them to what they're going to be in. Um, pH, salinity, all those things were brought up. And I think that's a very overlooked part of the quarantine process. Yes, you're trying to root out any silent invaders that could be hitchhiking into your tank, but you're also trying to get that animal acclimated to its new environment. Um, I man, that was just so well said and covered everything. So important on both fronts, though. The acclimation of your animal to a new environment that maybe the again pH, ammonia, salinity, any of these things might be uncommon to that animal or new. So we want to slowly bring them up to speed on how we run things here. Uh, in the meantime, yes, we're also rooting out all these possible infiltrators to our tank. But the two do go hand in hand. You're quarantining not only for the safety of your tank, but the safety of the animal you're about to put in it. So well said, well explained. Like it covered both ends of the spectrum that QT's absolutely vital for. As far as outside of the husbandry part and the captivity part, when we look at nature, there's going to be very few natural predators, which again sets up sea stars to either become invasive or just be really efficient. Um, with their regenerative properties, any injury sustained is usually non-fatal. A lot of animals will feed, if at all, on the tips of the asteroid's rays. So the again, kind of fingernails, I guess, the very tips. That seems to be the only part that has any nutritional value. The rest of it is basically just a calcium booster. You can see at the top of your screen, otter eating a sea star. He's really going to just chew off the tips of the rays and then toss the rest back down. And of course, as we'll talk about in a second, the reproductive and regenerative side of the animal is all still intact. So, very few natural predators. They do have the ability to blend in with cryptic, again, being different than aposematic coloration, where we're blending into our environment. Uh, we have some degree of toxicity. We're very spiny and unappetizing. It's a pretty, it's like the equivalent of, I don't know what the dating app is, where you are just swiping left or right constantly, like you're not interested and people aren't interested in you. Um, it's it's kind of one of those uh, general appearances that everyone's kind of agreed mutualistically. Hey, I don't want to eat you. You don't have anything to offer me, and you just want to do your thing. Um, so yeah, not a ton of natural predators, and if they are predated upon, it's usually out of like a freak occurrence or just for snack time type thing. Very rarely are these animals predated to the point where they actually die. And that all has to do with the regenerative properties and the reproductive properties of these animals. With the reproductive biology, they are gynochoristic. Uh, there's not a sexual dimorphism where we're going to be able to tell visually a male from a female. But again, gynochorism being one of at least two distinct sexes. That is your definition there. The gonadal tissue within the animal is prevalent throughout every single ray. Uh, and again, if we were in class, we could, of course, do a dissection. Um, they actually have quite a few if you do want to venture down this road, both YouTube videos and just science education forums in general have dissections of these animals. You can see the very obvious layers of taking off the digestive tract. Underneath that lies the gonadal tissue. And when these animals are ready to breed, the gonads will produce either sperm or egg to quote unquote copulate and propagate their species, but visually, without the dissection process, pretty hard to discern whether you have a male or female sea star. We've got here broadcast spawning. Here's where things get a little weird. And it's really up to the behavior. This isn't nearly as complex as we talked about with sponges, how they're broadcast spawners, but female sponges will basically inherit the sperm, deposit it within the mesohyl, and fertilize their own eggs internally. Here we've got, for the most part, across the species, usually just broadcast spawning. So males releasing sperm, females releasing egg. Hopefully they meet in the water. Cross your fingers, or your 5 fingers in this case. Wish for the best. As I said before, and it was mentioned, the food coloring example, it makes sense to aggregate in areas of low water volume. That way, there's less dilution of the sperm and egg as they meet. The notable exception, and by no means is it the only one, but it's certainly notable. Crown of thorns. Yes, I told you they'd be coming back up again and again and again. The chemosensory functions with some of these animals are really high up. Crown of thorns will release a chemical into water that attracts the opposite sex, not just the same species, or not just the species as a whole, but specifically the opposite sex within that species. So you're not bringing in competitors to breed. You're just attracting everything you can. What do they call that nowadays? The a thirst trap, I think, is the cool kid term. You basically are just attracting nothing but the opposite sex, and from what we know, members of your species of the same sex wouldn't even pick up on that signal. So you're just putting out a very notable signal for others to aggregate around you. This is what was mentioned earlier when we were talking about the bilateral larvae, being able to swim and exist kind of in that platonic state where you do kind of get lumped in with plankton or krill. Again, both being specific groups of animals, but you wind up being this thing that can be filter fed or absorbed by other animals, things like that. The flagellated look here, again, flagellated referring almost to that sperm-like appearance, very common. And then you're gonna, as was mentioned, absorb that right side and begin almost that torsion whirl into a 5-part body plan, as opposed to being bilaterally symmetrical. This, of course, indirect development. Those of you that have taken herps know about this, where this is going through metamorphosis. That's what indirect development is. It means that you're not born looking like the adult species. You have some form of change to go through in order to develop into that kind of adult form that we see with the 5-part body plan. With the asteroids that do exhibit some parental care, this is more analogous to what we talked about with the sponges, where females are, it's so tough, it's so tricky to define, because they're not necessarily broadcast spawning, but they do have the eggs typically on the outside of the body, so that they can be fertilized by sperm. And again, you got to figure an aggregation, tons of males, tons of females in a hopefully low water environment. And female keeps these clutches of eggs and extrudes them. It's basically like pulling. All right, I want to try another analogy. If you picture like a pearl necklace that you're holding in your hand and having the top sticking up out of your clenched fist and pulling it like that as it comes out bead by bead. That's basically the way they're going to extrude these eggs, pulling them almost in single file and then aligning them with all the rays on the female's body. This is going to typically happen in a lot, not only colder, but usually deeper environments. So this should make sense to you. The idea of broadcast spawning, if you're a deep water dwelling sea star, that doesn't hold a lot of water. That doesn't make sense. It makes much more sense to aggregate, kind of come together, so to speak, and male releases sperm, female draws out the eggs as they're getting fertilized, and then we'll hang on to them. If we're in that deep body of water, that makes a lot more sense to use the gonopores, which are the openings in which, again, kind of the top of your fist as you're pulling that necklace out, and extruding these eggs in order to be fertilized. Oops, sorry. That brings us to even more complicated fun stuff, asexual reproduction. This is very important that you understand the differences with fission versus regeneration. Because only one section here counts as asexual reproduction. It's almost like a very good backup plan. Just because the animal can regenerate doesn't mean it's asexually reproducing. The key element here is the central disc. You need a portion of it to get started. And the reason for that, let's look right here. You need that central disc portion because that's the start of the water vascular system. You need that ring canal to feed the radial canal. You can grow a new madreporite, you can grow a new stone canal, but you need some way to start filtering water in. So for example, in this picture, whatever happened to this poor animal, these two segments, they did not regrow a sea star. They didn't regenerate from that. That's just the ray itself being removed, and you can't come back from that type of injury. So that won't happen. Even if we had a separation here, it wouldn't necessarily mean the animal was asexually reproducing. It would just mean it regenerated. And that's where comet forms come in. Comet forms are unique. I would jot this down. It's definitely going to show up on an exam, whether on the midterm or the final. Comet forms are our only species known to perform autonomous asexual reproduction in their adult form. And that's going to come into play in a second. I'll tell you why. Autonomous means the intentional severance of, in this case, the severance of ray and a part of the central disc that becomes a new organism. Comet forms are the only species of sea star known to exhibit this behavior. And again, I know I'm probably repeating myself too much at this point, but I want it to hit home this much. Just because an animal is able to, let's say, as we talked about the North Pacific sea star, be chopped in half and regenerate and become two new organisms, that's not asexual reproduction. That's an awesome backup plan. That's awesome that you can regenerate like that, but you're not performing it as an asexual reproduction modality. It's a regenerative quality. It has nothing to do with reproduction. Comet forms are the only ones that perform this autonomous asexual reproduction. With the asexual reproduction aspect, there is something to be said about we've got a huge array of animals here. Something to be said about animals that can not only in their adult form autonomously reproduce, but in their larval form. And I think that can confuse people. But again, the thing I want you paying attention to is if nutrients are abundant enough, automation for asexual reproduction can occur at a variety of rates. And here, just for fun, because we've talked about them so much and they have to make another appearance, let's talk about real quick how crown of thorns develop. Anybody got any ideas where autotomy comes in with crown of thorns larvae?
Yeah, so they're one of the individuals that can actually like autonomize as larvae, and I one of the big things that's like a problem, they actually like consider them an outbreak, and they call them like an outbreak of crown of thorns, because like because they're broadcast spawning and like there's so many of them at a time. When they autonomize as larvae, it's like just thousands of them dropping to the seafloor at once, and it's the craziest. I tried to find like a video to link, but I couldn't get one pulled up. But it is like the craziest if you can actually like find a video of like what it looks like, and while they like explain it. um but I thought it was crazy that they actually call it like an outbreak as well.
Yeah, it's excellent and perfect terminology used. The outbreak of crown of thorns. Uh, Not only do we have an animal that's so efficient at decimating coral populations, instead of this comet form where we see the self-severance of part of the central disk and array, we have this bilateral, again, kind of flagellated sperm-like larvae. If nutrients are abundant, and again, they're probably abundant in a coral reef, it's arguably the most nutritious environment to be in. Instead of settling to the seafloor, they'll be able to perform fission and cut themselves in half, become two new organisms that continue eating. And as was mentioned just now, with this outbreak, the problem is you don't kind of see this whole process occurring. We're talking about very small organisms consuming all the organic particulate in the water, performing fission, separated into two. Those two become four. You know the math from there. And then all of a sudden they've eaten everything in that's free swimming or floating in that water, and then they all settle to the seabed at once. And it creates what we call an outbreak of crown of thorns. And whereas again, an already broadcast spawner has now given birth to, let's just say it's way more, but let's just say 100 babies. Now we have 100,000 babies all fall into the seafloor. They've eaten. It's like a plague of locusts. They've consumed everything in that environment, the free swimming pelagic area. Now they're all going to settle to the seafloor and start eating coral all at once. So you can literally visit a coral reef, see nothing, and then come back the next week, and there's 100,000 crown of thorns larvae just decimating the entire ecosystem. They're able to perform this fission in the larval form, which helps them be, I guess, unique and terrifying and awful to our environments, but really notable in that aspect. A lot of the times, again, with these comet forms, you're going to have to wait till that adult form to sever a limb and asexually reproduce. With crown of thorns, of course, the most invasive ones, you're able to perform that act of fission even in that larval form. As far as regeneration, the big key here is that central disc. You need a part of it to regenerate. So again, as was mentioned with the North Pacific sea star, pulling them out of the water, cutting them in half, and throwing them back, that just made two new sea stars. Yes, there'll be genetic clones of themselves, but we find at this kind of quote unquote primitive level, being a clone isn't a death sentence as far as genetic diversity. It's much simpler genetics. So it's not the worst thing in the world to have multiples in that environment with the same DNA or genetics. The reason for the centralized disc, and again, you got to figure in every one of these rays, it's the exact same thing as far as reproductive organs and digestive tract. So as long as there's enough nutrients stored within the individual ray and the part of the central disc, you're usually going to be able to regrow. A very efficient model for these animals and has served them well, obviously, throughout evolutionary history. I think he brought up a lot of great analogies and stuff I would have never touched on. So appreciate all the input today, all the engagement. That brings us to the end of asteroids. And again, I know it's weird that we're finishing with asteroids as far as the kind of invertebrate column, but back to that deuterostome development, they do wind up kind of being that evolutionary missing link between invertebrate and vertebrate life. So thanks, everyone. Hope you enjoyed it, and we'll talk soon.